Hello. Hello. Yes, hello guys, welcome on YourPedia platform. I hope you all are fine, preparing well. So guys, as you all know, we have started this particular series, NPTEL assignment, and we are covering more and more questions through this particular, NPTEL assignment for our GATE preparation. Okay, and guys, earlier also we discussed, Vijender sir discussed with you in detail, there is a very high correlation between those NPTEL assignment and previous year GATE questions. Okay, and guys, if you analyze that relationship, okay, and if you solve those problems, then easily your preparation, like for the upcoming examination, that will also be good if you will solve more and more previous year questions, and for a particular questions, if you will solve from the NPTEL assignment. Okay, so in today's class, this particular topic, Rankine cycle, is very important. Okay, slightly different also. Students generally feel that this topic is difficult. Okay, but this topic is very easy, because only some kind of concept building is required if you want to target this particular topic, Rankine cycle. Okay, nothing you need to remember, guys. Like, I feel like that is my general perception. I feel those topics are slightly difficult, in which you need to actually remember some data. Okay, but if you are targeting such kind of question, Rankine cycle, nothing you need to remember, only some concept you need to build. Okay, if you able to build those concept, entire data you will find in the question itself, and using that data easily you will be able to solve the problems related to Rankine cycle. Okay, so guys, in this class, like, first let me show you, actually I downloaded close to 14 assignment related to Rankine cycle from NPTEL website. And in those, out of those 14 assignments, I found 9 to 10 assignments very important. Okay, very relevant for our GATE preparation. Okay, so, and in out of those, 10 assignments, I have chosen 25 questions, 15 questions numerical based, and remaining 10 questions are what you can say, 1 marks question. Okay, yes, pura padenge bacho, like entire Rankine cycle we are going to discuss. What is superheating, how to solve problems related to superheating, how to solve problems related to regeneration, reheating. Entire Rankine cycle I am going to cover. And I can ensure you guys, if you attend this particular session, if you practice these 25 questions, easily you will be able to solve any previous year GATE questions from this particular topic, Rankine cycle. And in upcoming examination also, you will be able to solve problems related to Rankine cycle. Okay, chaliye. So first I'm going to discuss some brief with you, like what is Rankine cycle. Okay, how that cycle works, where we use, what are the different processes in Rankine cycle, basic about superheating, regeneration and reheating I will discuss, and then quickly we will move to the problems. Okay, very very important question, guys, we are going to discuss. Is that necessary? What is necessary? Complete padenge, yes, entire complete Rankine cycle we are going to discuss. So let me show you first the assignments. Okay, these are the NPTEL assignment, guys. Let me show you. Okay, something like this. Just a second. Chaliye. So these are the assignment, guys, something like this. You will find, okay, more than 109 question, 109 के आसपास questions हैं. Further, like we are going to share this particular file with you. You can practice, but if you solve those 25 questions, remaining 75 questions you will find very easy. Okay, so this file we are going to share with you. Don't worry about that. Okay, nothing you need to note, just you need to sit and you need to apply your mind. Okay, so it's my request to all of you guys, please sit with the, if you are having steam table with you, it will be good. Okay, because I'm going to share, I'm going to show here the data sheet like the saturated steam table and the superheated properties of a steam. That table I'm going to share with you. Okay, you will be able to observe that on the screen. But when I will change the page, okay, then sometime you can face some kind of difficulty, because I hope most of the students, they are having single phone only. On that same phone they are watching this lecture, and if you take some kind of screenshot of that table, then you will face some kind of difficulty in actually getting data from that screenshot. Okay, so it is good if you're having some steam table with you, just please sit with that. And calculator is must. Okay, so please sit with calculator and steam table. Chaliye, so these are the question, guys. 109 question we are going to discuss. Okay, and out of those 109 question, 25 questions I selected. So let us move to now those 25 questions. So, okay, before that, let me discuss with you some basics about the Rankine cycle. Guys, Rankine cycle is a vapor powered cycle. Rankine cycle क्या होता है? It is a vapor powered cycle we use in a steam turbine power plant. Okay, what do you mean by vapor power cycle, guys? In vapor power cycle, there is a change in phase of the particular medium is taking place. So steam we are producing from water. So water is converting into steam by utilizing the heat of the flue gases. So first we carry out the combustion in some kind of furnace. We burn some kind of fuel. Most of the time we burn coal, and by burning of that coal we produce flue gases, and by utilizing the heat of those flue gases we produce steam. Okay, and that steam further we expand into the turbine. Okay, steam turbine. And after expanding the steam into the steam turbine, we condense the remaining steam, waste steam, into the condenser. Okay, and by condensing that steam into the condenser, then again we circulate that saturated water, okay, into the what, again into the boiler using a pump. Okay, so four main components are there for any Rankine cycle or a thermal power plant. And what are those four components, guys? Number one is turbine, steam turbine. Second one is condenser. Third is your pump, and fourth one is your boiler. These are the four main components. But other than these four main components, guys, there are so many components. Okay, but those components, you this time, like if you want to draw the Rankine cycle, you need not to worry about all those components. Okay, there are various mounting, there are various accessories which are there in a typical thermal power plant. Okay, but these four components are very important: turbine, condenser, pump, and boiler. Okay, so what we are doing, guys, in single one line, if I will say what is a Rankine cycle, it is a standard cycle for a thermal power plant. Why we are saying standard cycle? Why not ideal? Because this is not a completely reversible cycle. This is only internally reversible. We assume that all the processes are only internally reversible. They are not externally reversible. So the ideal cycle for any heat engine is Carnot cycle only. Okay, so Carnot cycle, and Carnot cycle is not practically possible. So Carnot cycle, if I will draw something like this, like this is the saturation curve. So Carnot cycle is not practically possible. Something like this. Carnot cycle क्या होता है? Constant temperature, heat addition, then isentropic expansion, then constant temperature heat rejection, and then again isentropic compression. Something like this. Okay, but this is not possible practically. Carnot cycle is not practically possible. Why, sir? Here the pump is actually dealing with a two-phase medium, two-phase substance. You are having the mixture of liquid and vapor. So there is no such pump practically possible which can handle a mixture of liquid and vapor. Okay, similarly this particular expansion is also what that is known as wet expansion. Okay, so this type of turbine are also not possible. Okay, and even if you will carry out that kind of expansion, that is going to affect the turbine. So practically these type of systems are not possible. Okay, so Carnot cycle is not practically possible. That's why we consider it as an ideal cycle only. It is a reference cycle. Okay, generally just to compare how far away we are from the reversible cycle, completely reversible cycle. So standard cycle for any Rankine cycle is what? Rankine cycle. For any steam turbine power plant, the standard cycle is Rankine cycle. So guys, I told you there are four major components for any typical thermal power plant: turbine, condenser, pump, and boiler. So now if I will ask you, what are the four processes? What are the four ideal processes for boiler, for turbine, for condenser and pump? What is the ideal process for heat addition? Isothermal heat addition is not possible. So what is the ideal process for heat addition? Is constant pressure. What is the ideal process for expansion in the turbine? That is isentropic expansion, reversible adiabatic expansion into the turbine. Similarly, what is the ideal process for the condenser? That is constant pressure heat rejection. And similarly, what is the ideal process for pump? That is isentropic compression, means reversible adiabatic compression process. So guys, these four processes, like this is turbine. So one is the entry to the turbine, and two is the exit to the turbine, And what I told you guys, what is the ideal process? What is the ideal process for the turbine? Isentropic expansion. So that's why this 1 to 2, you can refer to here. This is actually TS diagram, temperature versus entropy diagram. Temperature versus entropy diagram. So this 1 to 2 is what? Isentropic expansion into the turbine. Because why? Because I told you this is the ideal process for turbine. Okay, isentropic expansion. But in real case, you are not going to get isentropic expansion. You will get non-isentropic expansion, which is known as irreversible adiabatic process, and that will be something like this. That will go something like this. Are you getting the idea, guys? So this, suppose this, if I will mark this point as 2 dash, so this 1 to 2 dash is nothing but irreversible adiabatic. Irreversible adiabatic. Are you getting the idea, guys? So this is ideal. This is ideal. But in real case, we are going to get irreversible adiabatic. And why actually I'm showing this irreversible adiabatic in this direction? Because the process is adiabatic. So process is adiabatic. There is no heat transfer. Okay. So entropy change of surrounding is 0. Why? Because the system is not interacting with the surrounding. So entropy change of surrounding is 0. But in any irreversible process, entropy generation will be positive. Entropy generation क्या होना चाहिए? Positive होना चाहिए. For any irreversible process, entropy generation will always be positive. That's why the system entropy is going to increase. It is must. It will increase in any irreversible process. That's why this 1 to 2, 2 will be in what? It will be in right of the this particular isentropic expansion. Are you getting the idea? So this is ideal one, but this is non-ideal. What you can say, non-isentropic or irreversible adiabatic expansion. Similarly, 2 to 3. This is this point to this point. 2 to 3 is the constant pressure heat rejection in the condenser. Rejection is required, guys. Why? Because it is not possible. Sometimes people like face this kind of question in the interview. If you will remove this condenser, simply the steam which is coming out from the turbine, if you will directly pump into the boiler, what is the problem? What is the problem? Like if you will pump the steam which is coming out from the turbine, if you will directly pump, even we carry out some kind of regeneration. We extract some steam and we mix it into the feed water, okay, to get the regeneration effect, to increase the mean temperature of heat addition. So what is the problem? Like if you will take the steam out from the turbine and directly supply that turbine steam into the boiler, okay, just to get the advantage, but that kind of cycle is practically possible. That is not possible, guys. Why? Because that is actually the violation of second law of thermodynamics. And practically also that is not possible, because if you are extracting steam directly from the turbine without condensing it, then the turbine exit pressure will be very high. Why? Because the turbine exit pressure is low just only because we are carrying out condensation. Because when we are carrying out condensation in the condenser, by carrying out condensation, we are maintaining the low turbine pressure. And by maintaining the low turbine pressure, we are creating the pressure difference between the inlet and outlet. And by creating that pressure difference only, we are getting the power. So if you will remove the condenser, there will be no pressure difference, there will be no power output, because that kind of heat engine is not practically possible. That is a violation of second law of second law of thermodynamics also. Why? Because a heat engine is not possible. You cannot develop a cyclic device producing work continuously while exchanging heat with a single reservoir. So if you will remove condenser, means if you will not reject any kind of heat, that cycle is not possible. So means we need to reject something, okay, but we are interested in rejecting minimum, okay, so that we will get maximum work output, efficiency will be more, okay. So this is the condensation process, guys. Phase change will be there. Constant pressure pe kya hoga? The ideal process is constant pressure, but in condenser, as the change in phase is taking place, so change in phase will always takes place at constant temperature and constant pressure. So this line is representing constant temperature, constant pressure both, okay. And again 3 to 4, this point 3 to 4 is what? Isentropic compression process. Yes, isentropic compression process. And again, if I will ask you guys, if the compression is not isentropic, how it will happen in real case? So in real case, this expansion will be something like this, again in this direction. So this point is what? 4 dash, okay. This point is 4 dash, again in the increase in entropy of the system, okay, entropy of the universe. Why? Because this process, this 3 to 4 dash 4s, this is showing us reversible adiabatic compression process. But in real case, you're not going to get reversible adiabatic, you will get irreversible adiabatic. So the entropy is going to increase, something like this, okay. And that's why we define some kind of what? Isentropic efficiencies for turbine and pump. We will discuss every single thing, guys. We are going to discuss in this class, whether it is related to isentropic efficiencies, regeneration numerical problem, every single type of question we will discuss. Okay, and some unique questions you are going to find. Okay, because I have not prepared those questions. I found those questions on the NPTEL platform only, but those questions are very, very good. Okay, if you will practice, surely that will open your mind. Okay, chaliye. So I hope you got the idea about this isentropic expansion, constant pressure heat rejection, isentropic compression, ideal case, and then constant pressure heat addition, guys. So this line is showing us constant pressure heat addition. And how heat addition takes place, guys? Heat addition in boiler, there are three parts. Lower part is the economizer, then you are having evaporator, then you are having superheater. Boiler part heat addition we define into three. Actually, there are three segments in boiler. First is the economizer part. Then evaporator means in evaporator the change in phase is going to take place, and in superheater you will superheat the steam. Superheated means if the steam coming out from the boiler at a temperature more than the T saturation. You know why this boiler is going to operate at some pressure. Okay, that is known as boiler pressure. So corresponding to that boiler pressure, you will have some T saturation. Yes or no? Simply by using the steam table, you can get that saturation temperature. For example, your boiler is operating at 5 megapascal. So corresponding to that 5 megapascal, you will have some saturation temperature. So if the steam is coming out at a temperature more than T saturation, means you are having the superheated steam. So don't worry about don't think he is going to give you are having the superheated steam at the exit of the turbine. For example, at 5 megapascal, the saturation temperature is supposed to 40. And somewhere he mentioned that steam which is entering into the turbine at a pressure 5 megapascal at a temperature 600 degrees Celsius. What it means? It means at 5 megapascal, the saturation temperature is 240, and you are getting the steam at the turbine inlet at temperature 600 degrees Celsius. It means you are providing the superheated steam. It means you need to draw the superheated Rankine cycle. Are you getting the idea, guys? So you need to think like what condition he is given what condition is given to you. So if the temperature is more than T saturation, guys, this is T saturation. Okay, this is T saturation. Corresponding to this boiler pressure, this is T saturation. And if the steam is coming out at a temperature more than this, it means that steam is superheated steam. Okay, so this actually the cycle which is visible to us, this is superheated cycle. Okay, superheated Rankine cycle. If there is no such superheated, suppose you are getting the saturated steam at the entry of the turbine, then this cycle will be something like this. ये cycle कैसा हो जाएगा? It will be something like this. Are you getting the idea, guys? So this is, suppose this point is 2 double dash. Okay, so 2 double dash to 3 constant pressure heat rejection, then 3 to 4 isentropic compression pumping process, then 4 to 6, that is a heat addition process in the boiler, then 6 to 2 double dash, that is expansion. So if it is mentioned you are having the saturated steam at the turbine inlet, so then you need to draw this some cycle something like this. Okay, but if you are having the steam at the entry of the turbine at a temperature more than T saturation, means you need to draw the cycle something like this, superheated Rankine cycle. Are you getting the idea? So these are the 4 processes in Rankine cycle. The ideal process for turbine is isentropic expansion. Ideal process for condenser is constant pressure heat rejection. Ideal process for pump is isentropic compression, isentropic pumping process, and the ideal process for boiler is constant pressure heat addition. And if you will draw all those cycles collectively, okay, you will have a Rankine cycle. It is actually a thermodynamic cycle, guys. What is the definition of a thermodynamic cycle? Any cycle which is a combination of various thermodynamic processes in which there is interaction of heat and mass with with changing state variables. Okay, and such that initial state is meeting the final state, that combination is known as a thermodynamic cycle. Okay, this is a power cycle. Why? Because from this cycle we are going to get some kind of power output. Okay, so it is a work producing cycle. That's why this cycle is what? This cycle is clockwise. Zoom kar दूं. Okay, let me zoom it for you. Okay, guys. So I'm giving you just basic idea about the 4 main components of Rankine cycle, thermal power plant, and how those different processes will look like in a typical TS diagram of a Rankine cycle. Okay, and what I told you guys, this Rankine cycle is not an ideal cycle. It is a standard cycle for thermal power plant. Why it is not ideal? Because in this we are not adding heat at constant temperature, so there are irreversibility. In this case, there are irreversibility in boiler, there are irreversibility in turbine also, condenser also, and in pumping process also there are irreversibility. Where are the irreversibility? When you are adding heat, suppose you are having the flue gases. Suppose these are the flue gases, guys. These are the flue gases. Flue gases are entering, okay, into the boiler, and you are utilizing the heat of these flue gases to you to produce the steam. So there is a temperature difference between these flue gases and the steam, and more is the temperature difference, more will be the irreversibility. So if you want to improve the efficiency for Rankine cycle, how we can improve? If we are able to decrease this irreversibility. And how we can decrease this irreversibility, guys? By increasing the mean temperature of heat addition. So if least is the difference between the flue gases and the temperature of the steam, the lesser will be the irreversibility, more will be the efficiency. And this temperature, mean temperature of heat addition, we can increase by regeneration, by superheating. Okay, these are the processes by which we can increase the mean temperature of heat addition. By increasing the boiler pressure also, you can increase the mean temperature of heat addition, and efficiency will increase. So separately also I will discuss with you what are the effect of all those parameters on the performance of Rankine cycle. Okay, chaliye. There is single superheater only. There is single superheater only. Reheater we use, Amit. Reheater we use two or more. Okay, it depends. Like what quality of the steam you will get at you want to get at the turbine exit. Superheater is one only. So this 6-to-1 process is what? This is a superheating process. 4-to-5, this is heat addition in the economizer. 5-to-6, heat addition in the evaporator, and 6-to-1, heat addition in the superheater. Okay, and this entire 1-to-6, this 4-to-6, 4-to-1 is the heat addition in the boiler, because these all are the part of your boiler only. Okay, but other than this TS diagram, guys, you can draw the PV diagram also, you can draw the HS diagram also. Okay, let me show you some idea about those diagrams, and then we will move to some problems, and through those problems further we will try to analyze more about this Rankine cycle. Okay, so time is very important. I hope you revise this topic earlier, and then some more you will be able to explore. But even if you have not revised this topic, then also you will be able to solve more and more problems. I'm going to discuss with every single basic concept with you, don't worry about that. So let me show you the PV and HS diagram also. So this is pressure volume. Here you are having pressure versus volume diagram, same for Rankine cycle. And this is HS, enthalpy versus entropy diagram. Okay, so this is a dome, guys. This we are drawing for water only, steam. Okay, so this is the dome, and this dome will slightly look like this for Rankine cycle on PV diagram. Okay, and these are the isentropic line. Okay, PV ki power, but isentropic compression, isentropic. Okay, PV ki power gamma equal to constant, something like this. Reversible adiabatic compression and expansion process. And these lines, on PV diagram we have these lines something like this. And these are the two constant pressure line. Constant pressure, constant pressure. Okay. One point is very, very important, guys, which you need to remember: the entry to the pump. Entry to the pump will always be saturated liquid. So this is the entry, guys. This is the entry to the pump. Saturated liquid. Okay. Here also you can analyze. This is the entry to the pump. This is the entry to the pump, and you are having saturated liquid. Then you will have isentropic compression, then constant pressure heat addition, isentropic expansion, then constant pressure heat rejection. Okay. Here also you can analyze this point. This is the entry to the pump. And then here on HS diagram, you will have isentropic compression. That's why you are having vertical line. Okay. And on HS diagram, you know how to draw the constant pressure line? Constant pressure lines are something like this, guys. These are the constant pressure line on HS diagram. Although, if you want to solve any question from Rankine cycle, previous year koi bhi question, if you want to solve, there is no such need. Okay, all those HS diagram and PV diagram. Only by using that TS diagram, you will be able to solve all problems. Okay, but as a mechanical engineer, when you are studying this particular topic, you need to aware about this HS diagram and PV diagram also. Okay, so the cycle is this is a dome on PV diagram, this is a dome on HS diagram. This is constant pressure heat rejection, constant pressure heat rejection in the condenser, then isentropic compression, constant pressure heat addition in the boiler, and then isentropic expansion process in the turbine, something like this. Here this is 1-to-2, this is 1-to-2 isentropic expansion, then constant pressure heat rejection in the condenser, then again isentropic compression and constant pressure heat addition in the boiler. Okay, so these are the constant temperature lines, guys. On PV diagram, constant temperature lines are something like this. Okay, so these are constant temperature line, something like this. Okay, so I hope you are having some basic understanding. Even don't worry, these are not required. Like we are going to solve 25 questions, and in any no, you're not going to find use of these diagrams on solving those 25 question, guys. Okay, so some basic understanding is required. If you able to get this PV and HS diagram, it's fine. Otherwise, this is much important. TS diagram is very important, and you need to very clear about this TS diagram. What are the various processes and how to draw the Rankine cycle on TS diagram, temperature versus entropy diagram. Okay, Aditya, this class is common. Rankine cycle is there in GATE thermodynamics also, GATE XC paper also. If you are preparing, if you are keeping this thermodynamics as one of your subject, and it is in mechanical engineering also. Okay, so this class we are covering for both XC and mechanical. Okay, चलिए let me show you the question number 1. Okay, so पहले जो 7 क्वेश्चन है, these are very important, very important 7 questions. 7 का सेट है ये, फर्स्ट 7 क्वेश्चन बहुत इंपॉर्टेंट है, and you will be able to analyze much more detail about the Rankine cycle. Okay, and you will get the confidence, yes, I can solve problems related to Rankine cycle. तो 7 क्वेश्चंस है, फर्स्ट 7 क्वेश्चन, these all are common data question, guys. सभी के सभी कॉमन डेटा है. Okay, so let me first read here the data which is common for all first 7 question. And guys, it's my request to all of you, don't sit ideal. Please have some kind of calculator, notebook with you, and try to practice more and more. Chaliye. So this is question number 1. The data is same for all question number 1 to 7. A steam power plant operated on a Rankine cycle with the superheat has a high pressure of 5 megapascal. High pressure means, guys, the boiler pressure. High pressure कौन सा होता है? Boiler pressure. Low pressure is the condenser pressure. So the boiler pressure is 5 megapascal and a boiler exit is 600 degrees Celsius. Boiler pressure is 600 degree Celsius. Now what you need to check? You need to check at 5 megapascal what is the T saturation. If the T saturation is 600, means you are providing the saturated steam to the turbine. But if this temperature 600 is more than the T saturation, means you are supplying the superheated steam to the turbine. Very easily, by observing the property table, you will be able to conclude that. Okay, the boiler receives heat from a heat source at 700 degrees Celsius. So the flue gases are available to us at a temperature 700 degrees Celsius. We are utilizing the heat of those flue gases. The ambient temperature is 20 degrees Celsius. Provide cooling in order to maintain the condenser at 45 degrees Celsius. So we are maintaining the condenser at 45 degrees Celsius. All components are ideal. All components are ideal except for the turbine. The turbine is not ideal. Okay, which has an actual exit state with a quality 97%. Very important point, guys. Which has a actual exit. Actual exit, guys. Actual exit means the turbine expansion in the turbine is not isentropic. That expansion in the turbine is non-isentropic, means irreversible adiabatic with a quality 97%. So this is the dryness fraction. Dryness fraction of the steam at the exit of the turbine 97%. So the steam is 97% dry. Okay, 3% are vapor particle, vapor are there in that steam. The process is, in all the 4 processes are steady state flow process with negligible changes in kinetic and potential energy. Assume the pump handles incompressible liquid. So this is the volume handled by pump. Okay, volume handled by pump. How much is it? It is a volume handled by pump. Specific volume handled by pump. This is also given to us. Okay, I hope you noted down all these important data. अब देखो इस डेटा को जैसे ही आपके सामने आए, if you observe this data, first you need to draw the Rankine cycle, guys, something like this. आपको सबसे पहले तो क्या देखना चाहिए? Property table देख लो, something like this. Suppose this is the property table. Let me zoom it for you. Okay, so this is a property table. So at 5 megapascal, if you will observe, this is the T saturation, 263.99 degrees Celsius. 263.99 degrees Celsius. This is a T saturation at 5 megapascal. Okay, 5 megapascal means 5 megapascal को क्या लिख सकता हूं मैं? 5 megapascal या 5000 kilopascal. Okay, and you are supplying the steam at a temperature 600, means you need to draw the superheated Rankine cycle. Okay, now let me draw here the superheated Rankine cycle. So that you will be able to locate all those points here, something like this. So this is the entry to the turbine, guys. This is the entry to the turbine. This is the entry to the turbine. Okay, something like this. So this temperature is 600 degrees Celsius. Pressure is 5 megapascal. Okay, pressure is 5 megapascal, and here this is our isentropic expansion. Okay, but in actual case we are not having isentropic expansion, we are having non-isentropic expansion. So let me show that the non-isentropic expansion, something like this. Okay, something like this. So this is condenser exit, then isentropic compression. Okay, then constant pressure heat addition, something like this. So you are having a cycle something like this. आपका जो cycle है, the cycle will look like something like this. Okay, so this is point 1, point 2, 2s. Okay, this is 3, this is 4, and this is 5. Okay, and let me mark this point as, this particular point as 2. Okay, this point is 2, this point is point 2. So non-isentropic means irreversible adiabatic expansion into the turbine, something like this. So this temperature is given to us 45 degrees Celsius, the condenser temperature. This is temperature versus entropy diagram. So I hope you all are able to draw this Rankine cycle. Now let us see what he is asking you in this first question. पहले क्वेश्चन में आपसे क्या पूछ रहा है? The specific heat transfer to the boiler from the heat source. How much is the heat transfer to the boiler from the heat source? Okay, very simple question, guys. How much is the heat transfer? So let me take it here. Guys, this process is the heat addition process in the boiler. 4 to 1 is the heat addition in the boiler. 4 to 5 heat addition in the economizer. 5 to 6 heat addition in the evaporator, and 6 to 1 is the heat addition in the superheater. Okay, so if I will write it here, H1 minus H4, what is this? This is heat supplied. H1 minus H4. H1 is the enthalpy at the exit of the boiler. H4 is the enthalpy of the water at the entry of the boiler. Okay, and H1 minus H4 is the heat supplied in the boiler. So if you able to get this H1 minus H4, you will get the heat supplied. Are you getting this idea, guys? So this is enthalpy of the water at the exit of boiler. This is or exit of boiler or entry of the turbine, because exit of boiler and entry of the turbine both are same. Yes, Nitesh, you need to watch live this video. Okay, so this is point 1, this is point 4, and 1 to 4 is the heat addition in the boiler. Okay, this is heat supplied in the boiler. So heat supplied is nothing but H1 minus H4, specific heat addition. What is H1, guys? H1 is the enthalpy of the superheated steam. From where you will get this? H1 कहाँ से आएगा? H1 you are going to get from the saturated steam table or superheated steam table. कहाँ से मिलेगा? Where this point is lying? This point is lying in the superheated region. That's why H1 you are going to get from the superheated table. So let me show you here. These are the two tables, guys, which are given to us. This is for the saturated water. Okay, saturated steam and water. Okay, saturated steam and water. Saturated steam and water. The upper table is for saturated steam and water, and the lower table is for what? Superheated water, superheated steam, but because this is actually, these all properties are for water only, that's why the water is mentioned here. Okay, so superheated water. Okay, what pressure, guys? What is the boiler pressure? 5 megapascal. So this is 5 megapascal, means 5000 kilopascal. Temperature 600 degrees Celsius. So this is the enthalpy which is directly given to us, 3666.47. This is the enthalpy at the entry of the turbine. From where we are getting this idea, guys? I told you, if the temperature at the entry of the turbine is more than T saturation, means you are having superheated steam. As you can check here, at 5 megapascal, the T saturation is 263.99. Okay, so this temperature, guys, this temperature, this particular temperature, this is 263.99 degrees Celsius. But you are supplying the steam at a temperature 600 degrees Celsius, means you need to enter into the superheated region, then only you can have this temperature. And that actually that basic thing we generally discuss in properties of pure substances. If the temperature is more than T saturation, you are in the superheated region. If the temperature is less than T saturation, you are in the subcooled region. As you can check, the temperature is more than T saturation, means we are in the superheated region, and in the superheated steam table, this enthalpy is directly given to us. So we can mark here, this is H1. 3666.47. Okay, so H1 is nothing but 3666.47 minus H4 equal to heat supplied. Now the question arises, from where you will get H4? From where you will get H4? This H4, enthalpy at the entry to the boiler. Enthalpy at the entry to the boiler. This is in the subcooled region, guys. Okay, and in subcooled region, okay, at this particular, we don't know what is the temperature here. So from that subcooled or superheated table, we cannot write this directly, but we know one formula: the pump work, the WP, neglecting kinetic and potential energy changes, neglecting kinetic energy and potential energy changes. WP. What is WP? It is nothing but H4 minus H3. The pump work, isentropic compression process. Isentropic compression process, pump work, neglecting kinetic and potential energy changes, no heat transfer. Why? Because the process is ideal isentropic compression, means reversible adiabatic process. So there is no heat transfer. Okay, so the pump work will be enthalpy at the exit of the pump minus enthalpy at the inlet of the pump. Okay, so if you want to find out H4, so H4 is nothing but WP plus H3. H4 equal to WP plus H3. Okay, now from where you will get the H3, guys? What is H3? हमेशा आपको रिमेंबर करना पड़ेगा बच्चों. Always just remember, always mark entry to the turbine as 1, exit to the turbine as 2, exit to the condenser as 3, and 4 as the exit to the pump. Something like this. If you use this sign, then it will be easy for you. So H3 is nothing but HF. HF at P condenser. What is H3? Where this point is lying, guys? This point lies in the saturated liquid line. Okay, this point, this is your critical point, and this particular line is your saturated liquid line. This is your saturated vapor line. So H3 is nothing but HF at T condenser. So if you'll observe it here, at 45 degrees Celsius, at 45 degrees Celsius, because it is given to us the condenser temperature is 45 degrees Celsius. So at condenser temperature, this is P saturation, means this is P condenser. This is boiler pressure, guys, pressure boiler. This is pressure condenser. Okay, high pressure, low pressure. This is temperature condenser. This is temperature T saturation in the boiler. So at this temperature, what is HF? This is 188.42. 188.42. Okay, so if you will put it here, 188.42. Okay, so H4 equal to WP. What is WP, guys? What is WP? Can I write this WP as VDP? Yes or no? Pump work is equal to VDP. What is V? The specific volume that pump is handling. For any open system, we write the work as VDP, neglecting those kinetic and potential energy changes. So pump work, we can write it as VDP, where V is the volume that pump is handling and DP is the change in pressure in the pump. Okay, so how much volume it is handling, guys? This is given to us. Let me check it here. The data which is given to us, the specific volume which this pump is handling, 0.00101. Okay, 0.00101. So you can write it here, 0.00101. Okay, this is the specific volume which this pump is handling. Okay, how much is the change in pressure in the pump, guys? Kitna pressure? How much pressure change is there in the pump, guys? That will always be the boiler pressure minus condenser pressure. Boiler pressure minus condenser pressure, because pump is going to provide the saturated liquid at a pressure equal to the boiler pressure. Because exit to the pump is what? In general case, exit to the pump is what? Boiler. Okay, so exit pressure to the boiler is boiler, exit pressure to the pump is boiler pressure, and inlet pressure is what? Condenser pressure. So here you can write 0.00101. What is the boiler pressure, guys? It is 5000 kilopascal. What is condenser pressure? That easily you will get from here. Condenser pressure corresponding to 45 degrees Celsius. What is P condenser? What is P saturation? Corresponding to 45 degrees Celsius, guys, this is given to us 9.593. So if you will put this data here, 9.593, all data I am taking it in kilopascal. So kilopascal multiply by volume, specific volume in meter cube per kg, so that you will get work in kilojoule per kg. Specific work, we are going to get pump work, specific work in kilojoule per kg. Are you getting the idea, guys? So please solve and you will get the pump work. Okay, now I'm expecting some answer from you, because pump work we know पंप वर्क हमारे पास आ जाएगा, पंप वर्क प्लस H3 you will add, you will get H4, and simply if you will put this value here, this minus H4, you will get the heat supplied. So there are four options in front of you, चार options है. Let me show you here. These are the four options for the question number 1, the specific heat transfer to the boiler from the heat source. So four options, option A, B, C, D. Try to answer, guys. Most of the part I already solved. Okay. Step by step, we will move to all different type of question, guys. What I told you, in this question, we are having 7 questions. All are unique, all are different. Okay. Try to practice. Apna speed boost up karo. And you will find question number 8, 9, 10 very beautiful. Okay. But I cannot move to directly to those kind of questions. First, we need to build some kind of basic concept. Chaliye. So let me write it here. This particular data in front of you, so that we will be able to, okay, all different type of student will get the idea. So 5000 minus 9.593 multiply by 0.00101, so I'm getting 5.04 kilojoule per kg. 5.04 kilojoule per kg. So this you need to put it here. H4 equal to 5.04 plus 188.42. So H4 will be 188.42. So 193.46 kilojoule per kg. Okay. Now put this value here. 3666.47 minus answer karoge, you will get heat supplied. This answer, heat supplied, you will get heat supplied in the boiler 3473.00 kilojoule per kg. This is a heat supplied in the boiler. I hope you all are getting this answer, guys. Very simple, very easy question. Okay, मेरे ख्याल से सभी के सभी बच्चे all are able to find out this answer, guys. So let me show you now the question in front of you. So guys, this is the common data which is given to us. I hope you all note it down. ये बहुत इंपॉर्टेंट डेटा है बच्चों. पहले 7 क्वेश्चन के लिए, all first 7 questions are common data question. So don't miss this data. Okay, because I will not be able to show you again and again this particular data, guys. I hope you can understand. So time is very important for us. So please note it down, this important data. So we solved this question and we got this first answer 3473. The heat supplied to by the heat source is what? 3473 kilojoule per kg. This is the answer for the question number 1. Very good, guys. Some of the students are getting this answer. Very good. 3473 kilojoule per kg. Now let us move to next question, guys. Next question पे move करते हैं. The specific work output of the actual turbine. Very good question. बहुत अच्छा question है. Second question, the specific work output of the actual turbine. Guys, he is asking you the specific work output of the actual turbine. What is the specific work output of the actual turbine? What do you mean by actual turbine, guys? What do you mean by actual turbine? Actual turbine means something like this. Okay, something like this. So this is a point here. So this is isentropic expansion, but we are having non-isentropic expansion, something like this. One, two, three, four. Why actually I'm showing this diagram something like this? Why? Because it is given to us. The expansion is non-isentropic. Why? Because in actual turbine, the turbine expansion is not ideal. If it is not ideal, what type of expansion you will get? You will get adiabatic, irreversible adiabatic. And I already explained you, for irreversible adiabatic, you will get a process something like this. So now what we want, guys? What we want? We want, for this question, if you want to find out the turbine work, actual turbine work, so this is nothing but H1 minus H2. This is nothing but H1 minus H2. Again, H1 is given to us, guys. What is H1? H1 is 3666.47. 3666.47. From where we are getting this H1? What is this state? This is 5 megapascal, 600 degrees Celsius. So this is a point which lies in the superheated region. This point, the entry to the turbine lies in the superheated region. Very good, John. John Wick ka like fastest answer we got from the John Wick. Very good. 1155.12. This is a specific work output for this question. Very good. So guys, this is the enthalpy at the entry of the turbine which is given to us, and you can easily get this data from the superheated table. Okay, superheated table. So this is the boiler pressure. At this boiler pressure corresponding to this temperature, we are having enthalpy 3666.47. Now the question is very easy. If you are able to find out this H2, you will get the answer. So guys, where this point lies? This point lies in the wet region. This point two lies in the wet region. And how we write enthalpy in the wet region, guys? Enthalpy in the wet region we can write very easily. Enthalpy in the wet region we can write very easily as HF plus X HFG. So this is a formula to find out enthalpy in the wet region. H2 equal to HF plus X HFG. What is X? X is the dryness fraction at the exit of the turbine, and this is given to us. The actual quality of the stream at the exit of the turbine is what? 0.97. 97% is the quality of the steam that is given to us. Okay, so this is 0.97. This is given to us. What is HFG, guys? HFG at what? What is this? This is the condenser pressure. So corresponding to condenser pressure, if you check this particular table, you will get HFG. Okay, this particular table, guys, if you will check, corresponding to condenser pressure, this is condenser pressure, this is condenser temperature. So this is HF 188.42 and this is HG 2583.919. Okay, so if you put this data here, agar ye data aap yahan put karte ho, so you will get the idea. Let me put it here. HF H2 is equal to HF. What is HF? HF is 188.42 plus X into Hg minus HF. So Hg is 2583.19 minus 188.42. Okay, this is actually plus, guys. मैं थोड़ा सा इसको दोबारा लिख देता हूँ so that you will have more clarity. So 188.42 plus 0.97. Okay, so please try to solve and you will easily get H2 enthalpy at the exit of the turbine. So let me solve it for you. This is Hg, guys, this is Hg, this is HF, and Hg minus HF is what? That is latent heat of vaporization, HFG. Okay, so 2583.19 minus 188.42 multiply by 0.97 plus 188.42, you will get 2511.3469 kilojoule per kg. So now what is W turbine? W turbine क्या होगा बच्चों? This will be H1. H1 is 3666.47. This is H1 minus H2. It is 2511.3469. So if you solve this, you will get the W turbine. But this is not W net. This is W turbine. This is not W net. W net is what? W turbine minus W pump. So if you will subtract 5.0 from this, you will get W net also. Why? Because in question number 1, we calculated the pump work. Question number 1 में हमने pump work calculate किया था. So this is pump work, guys. 5.04. So the turbine work minus pump work, that is going to give us net work. Okay, but in this question, he is not asking you net work. He is only asking you the turbine work. Okay, so let me subtract 3666.47 minus answer. You will get 1155.123 kilojoule per kg. Very good. Very good, guys. So this question, the right answer is option C. Option C is the right answer for this question, guys. Very good, guys. Lots of students are now getting this answer. 1155.123 kilojoule per kg. Let us now move to question number 3, guys. Question number 3. If the actual turbine is replaced by ideal one, if you will replace the actual turbine by the ideal one, actual turbine को अगर आप ideal से replace कर दें, that operates between the same boiler exit state and the same condenser pressure, what is the specific work output of the ideal turbine? What is the specific work output of the ideal turbine, guys? if you will replace the turbine, the actual turbine with the ideal turbine means so that you will get isentropic expansion, reversible adiabatic expansion. So if you replace that actual turbine with ideal turbine, what will be the work output of that ideal turbine? That he is asking you. Even for this question, you need not to solve. Why? Because the isentropic work will always be more than the actual work. For any work producing device, the isentropic work will be more than the actual work. Are you getting the idea? So in earlier case, we got the answer 1155. So in ideal case, you are going to get work more than this, and there is only one option which is representing work more than this. So directly only you can say the answer is this, D, 1371. Why? How actually I can say? Because the ideal work for any work producing device will always be more than the actual work. Okay, but let us find out this answer, 1371 kilojoule per kg. So from where you will get this answer, guys? Let me tell you. So now let me draw it again, the Rankine cycle. If you draw it something like this, guys, with me, easily you will get idea about this Rankine cycle. 5-6 बार draw करोगे, you will get practice. Okay, easily. So this is a cycle diagram, something like this. Now we are having the expansion in the turbine, something like this, guys. So we are having expansion something like this. This is point 1, this is point 2, this is point 3, and you will having a cycle something like this. Something like this you are having cycle. Point 2, point 3, point 4, point 5, point 6. Okay, this is Rankine cycle with ideal turbine. We replace the actual turbine with ideal turbine. So what do we want, guys? We want turbine ideal. W turbine ideal means this is nothing but H1 minus H2. Let me mark this point as 2s because 2 तो मैंने already mark कर दिया था. 2 I marked for what? 2 I marked for this. This point I'm already marked with 2. So now let me mark this point as 2s. This point as 2s. Okay, isentropic expansion. So what do we want, guys? We want H1 minus H2s. H1 minus H2s. So H1 is same. This we know from the superheated table. This superheated table, we know H1 is nothing but 3666.47. But what is, from where you will get HS2? Again, this is in the super wet region. This point 2s lies in the wet region. And how to write the enthalpy in the wet region, guys? Enthalpy in the wet region, H2s, we can write it as HF plus X HFG. HF plus X HFG. But what is the problem in this question, guys? In this question, in this part, we don't know what is the dryness fraction. He, like earlier, he has given you in actual turbine, with actual turbine, the steam quality which you are going to get at the exit of the turbine, that is 97%. So 97% is the quality at the exit of the turbine with actual turbine. But we don't know what is the quality you are going to get with the ideal turbine. So we don't know X. So first you need to find out X. If you want to find out this H2S, you need to find out this X. And from where you will get this X, guys? For that, you need to equate entropy at point 1 and 2, 2s. Why? Because this is isentropic process, reversible adiabatic expansion process. Are you getting the idea, guys? Reversible isentropic expansion process. So here, what is S1? S1 is the entropy for the superheated steam. So from this superheated table, the steam which you are having at a pressure 5 megapascal, at a temperature 600 degrees Celsius, with this enthalpy, with this entropy. So this is the entropy at point 1. This is the entropy by which steam is entering into the turbine. So this is nothing but S1. Are you getting the idea, guys? This is specific entropy at the entry of the turbine, 7.2588. So let me write it here. 7.2588. So this is nothing but S1. Okay, and S1 is equal to what? S2. S1 equal to S2. S2S, sorry. S1 equal to S2S. S1 equal to S2S. And this S2S point, 2S point lies in the wet region. And in wet region, how we can write the entropy, guys? We can write the entropy as SF plus X SFG. So this 2s, entropy at point 2s, we can write it as SF, entropy here at this particular point, plus X into SFG. And all these data you will get from the property table, saturated water and steam property table, because this point lies in the wet region. Okay, so here at condenser temperature, condenser pressure. So this is SF, this is SG. SF, SG both are given to us. If you'll put this data, you will get the quality of the steam at the exit of the turbine. So let us put all this data here. 7.2588 equal to SF. What is SF? This is SF. At condenser pressure, what is SF? 0.6386. 0.6386 plus X into SFG. What is SFG? SG minus SF. What is SG? 8.16, 8.1647 minus 0.6386. 0.6386. So let us put all the data and you will get the X value. Okay guys, easily you will get the X value. So 7.2588 minus 0.6386 divided by 8.1647 minus 0.6386. So I'm getting 0.8796, 0.8796, and obviously it will come out less than 0.97. 0.97 से कम आएगा बच्चों, because the 0.97 with irreversible adiabatic. No, Jairam, you're making some kind of calculation mistake. You will get 0.8796. Please check it again. 0.8796. This is the quality at the exit of the turbine with ideal turbine. With ideal turbine, you are going to get X 0.8796. Now, if you will put this data here, because if you want H2S, अगर आपको H2S चाहिए, so H2S is nothing but HF plus X into HFG. Okay, so what is HF? HF is the enthalpy at the condenser pressure for the saturated liquid, 188.42. So let me put it here, 188.42 plus X into HFG, which is 2583.19. 2583.19 minus 188.42. So this is H2S. And how much X we calculated, guys? X we got the value of this X equal to 0.879632. So if you put this value, you will get H2S. Enthalpy at the exit of the turbine with isentropic expansion, reversible adiabatic expansion. So let us solve this. 83.19 minus 188.42 plus 188.42. So you will get 2583.19 kilojoule per kg. Okay guys, now if you'll put this data here, what do we want? We want the ideal work. We want the ideal work. W turbine ideal. So that is nothing but H1 minus H2S. So H1 is 3666.47 minus H2S, and H2S we go to the value 2583.19. So let us subtract this from this. 47 minus answer, you will get 1083. Okay, I think let me check it again. Okay, actually, how you can get this? Because I missed this data. So 2583.19 minus 188.42 multiplied by 0.879632 plus 188.42. So you will get this 22. This value H2S will come out 2294.9363 kilojoule per kg. Please check again, guys. दोबारा एक बार चेक कर लेना. 2294.9363. This is the data you are going to get. 2294.9363. And if you put this data here, 2294.936, you will get the ideal work. So 3666.47 minus answer, you will get 1371. Exact answer you will get, guys. 1371.53 kilojoule per kg. This is the ideal work you are going to get. This is the ideal work you are going to get, guys. Please check and confirm. I hope you all are getting this answer, guys. Very good. Slowly we are moving, guys. Slowly we are moving. We calculated how much is the heat supplied in the boiler, how to calculate that heat supplied in the boiler. Now we go to the idea how to find out the turbine work. Ideal case also, and in case of non-ideal case means irreversible adiabatic. So if you are getting the expansion irreversible adiabatic, then how to calculate the work? And if you are getting the reversible adiabatic expansion, then how to calculate the work? Okay. And what is net work? Net work is turbine work minus pump work. I hope this is clear to you. So this is the ideal work. Now next question is very easy. Very easy. And in seconds you will get the answer. Seconds mein aapka answer aa jayega bachcho. Now in this question number 4, he is asking you what is the isentropic efficiency? What is the isentropic efficiency of the turbine? What is the isentropic efficiency, guys? So let me tell you here, for any expansion work producing device, so suppose these are the two constant pressure lines, something like this. So मैं आपको ऐसे शो कर देता हूं. So cycle पे something like this. So this is the expansion initially we got ideally, and this is the expansion you will get actual. Okay, and this is your condenser. This is 0.2s, this is 0.2, this is 0.1 ideal. Okay, so this is what this is slightly inclined line, guys. This is vertical line. ये vertical line है, this is inclined line, and again you will have a vertical line something like this, constant pressure something like this. So the cycle will be something like this. Okay, so this is temperature versus entropy diagram. So the isentropic efficiency of the turbine, isentropic efficiency of the turbine is nothing but actual work divided by isentropic work. Actual work divided by isentropic work. Okay, or I can write it as H1 minus H2 divided by H1 minus H2S. So for turbine, the isentropic efficiency is, for turbine, the isentropic efficiency is the, this efficiency actually tells us about the deviation from the isentropic expansion. How much is the deviation from the isentropic expansion? If the isentropic efficiency is very high, means the deviation from the isentropic expansion is very less. But if the isentropic efficiency is very low, it means there is a huge deviation from the ideal expansion. So this is nothing but the actual work obtained by the turbine divided by isentropic, means ideal work, maximum work obtained by the turbine. So this is H1 minus H2, actual work obtained. This is H1 minus H2S. Okay, why? Because this is the actual expansion. Okay, let me mark it here. ये क्या आपका irreversible adiabatic. Irreversible adiabatic. What is this? This is reversible adiabatic. Reversible adiabatic. Ideal. Okay, so very easily you will get the answer if you will put the data 1155 divided by 1371 multiply by 100, you will get the isentropic efficiency. You will get the isentropic efficiency of the turbine. Okay, so just put this data 1155 divided by answer, you will get 84.2. 84.2%. 84.2% is the efficiency, isentropic efficiency of the turbine, guys. 84.2% is the isentropic efficiency of the turbine. So right answer is option A. Option A is the right answer for this question. Okay, chaliye, let's move to next question. Question number 5. What is the thermal efficiency of the cycle? Now, very good question. These type of questions also you are going to find. Question number 5. What is the thermal efficiency of the cycle? What is the thermal efficiency of the cycle, guys? Very easy, very simple question. Now I think you all are maintaining that pace, and I'm getting answer also from your side. That is good. Great. Chaliye, I hope you all are participating. Good. So thermal efficiency of the cycle is what? How we can define the thermal efficiency, guys? The thermal efficiency is nothing but thermal efficiency of Rankine cycle for any heat engine, okay, or any work producing device. We write the cycle efficiency as W net divided by heat supplied. The thermal efficiency of Rankine cycle or any cycle from which you are getting any kind of work output, that is W net by heat supplied. So what is W net? W net is nothing but W turbine minus W pump divided by heat supplied in the boiler. So what is mentioned? Calculate the thermal efficiency of the cycle with actual turbine. So here you need to write what? You need to write the actual turbine work, not isentropic. Means you need to use here 1155. Guys, you can get this question separately also. Okay, separately if you will get, first you need to calculate the turbine work, you need to calculate the pump work. The process is going to remain same. Like how we calculated in question number 1, question number 2, the process is going to remain same. So if you will calculate the turbine work, if you will calculate the pump work, if you will just take the summation of those, you will get the network. Network divided by heat supplied, that is known as cycle efficiency. Okay, so just put all those data. Turbine work is what? Actual turbine. This is actual turbine work. So this is given to us and we calculated actually 1155. Pump work is close to 5.04 and I think this we got 3473. Let me check. I don't know what actually we got. This we calculated in the question number 1. 3473. 3473. This is the heat supplied in the boiler. Heat supplied in the boiler is 3473. How to calculate? The process is going to remain same. So I'm not discussing again with you how to calculate that heat supplied in the boiler. So if you are facing any kind of question in which is asking you to calculate the cycle efficiency, so use this formula. The cycle efficiency is nothing but the W net by heat supplied. W net is turbine work minus pump work divided by the heat supplied. And if you put all those data, you will get the cycle efficiency. Very good, Prashad. Prashad Naga, your answer very right. So 11,1155 minus 5.04 divided by 3473, you will get 33 multiplied by 100. Let me write it here. Multiply by 100. You will get 33.11%. 33.11%. This is the cycle efficiency you are going to get. And yes, it is in the typical range of the efficiency of Rankine cycle. Rankine cycle, they are having very low efficiency in the range of 30 to 40% only. And we are getting efficiency in that range only, 30 to 40%. So this is the cycle efficiency. So what will be the answer, guys? For this question, the answer is what? The option C is the right answer, 33.2. We got answer very close to this. Okay, if you will check, that is very close to this, 33.11. So this is the answer. Okay. Now let us move to question number 6. Question number 6. The specific heat rejection in the condenser. How much is the specific heat rejection in the condenser? So he is asking you heat rejection in the condenser. How much is the heat rejection in the condenser with actual turbine, guys? With actual turbine. So let me write it here directly. So Q rejection is nothing but H2 minus H3. Can I write something like this? Heat rejection in the condenser is nothing but H2 minus H3. What is H3? That is HF 188.47. 41, sorry. This is this HF, sorry, this HF 188.42. So this is 188.42. Okay, so this is H3. What is H2? H2 we calculated. If you will check it here, H2 we calculated. Let me check it here. In second question, we calculated H2 2511.3469. And you know, guys, how to calculate this H2? The process is same. Chaitanya, Vijay Raju, why dryness fraction is deviating? Let me tell you. So this is the expansion. Let me zoom it for you so that you will get more clarity. Guys, this is the ideal expansion. ये कौन सा expansion है? This is the ideal expansion. This is the ideal expansion. Ideal expansion means isentropic. Means here if I will mark 2s, so if I will mark it here 2s, so this is reversible adiabatic expansion. It means S1 equal to S2s. S1 equal to S2s. These 2 points, they're having same entropy. So this is a reversible adiabatic expansion. But in case of irreversible adiabatic, this is irreversible adiabatic. So I told you, in case of irreversible adiabatic process, that there is no heat transfer. So the entropy change of the surrounding will be 0. Entropy of the system is going to increase. Why? Because the process is irreversible. And in any irreversible process, there must be entropy generation. So if you want to get that entropy generation, means if there is entropy generation, so entropy change of the system will always be positive. Why? Because entropy change of the surrounding is 0. So to get the entropy change of the system positive, this point 2 will always be in the right of this point. Okay, and if you will move this point in the right of this, in which direction you are moving? You are moving in the increase in dryness fraction. Why? Because here at this particular line, saturated liquid line, the dryness fraction is 0, and at this particular line, saturated vapor line, the dryness fraction is 1. So when you are moving in the right direction, so the dryness fraction is going to increase. That's why when we got the ideal expansion, we got the dryness fraction 0.87, and when we are getting the actual expansion, the dryness fraction is close to 97%, means 0.97. Are you getting the idea? Yes. Okay, I hope Vijay Raju, it is clear to you now why actually why the dryness fraction is increasing in case of irreversible adiabatic. Okay, chaliye. So 2511.3469. 2511.3469 मेरे ख्याल से यही था. You can also check, आप भी check कर लेना. So 2511.3469 minus 188. 2511.3469 minus 188.42. You will get 2322. You will get 2322.9269 kilojoule per kg. Okay, so the right answer is what? Option B is the right answer. Option B is the right answer. This is the heat rejection in the condenser. Guys, this you can find out from this also. आप इसको यहाँ से भी निकाल सकते हो. Net heat transfer, Q net equal to W net. Q net equal to W net. Okay, so Q net is what? Q net is heat supplied minus heat rejection equal to W turbine minus W pump. So this is nothing but 1155 minus 5.04, because we calculated all those things. So heat rejection equal to heat supplied. Heat supplied is 3473 minus 1155 minus 5.04. So if you will check from this, then also you will get the same answer. Okay, Q net for any closed system, Q net equal to W net. Q net is heat supplied minus heat rejection. W net is W turbine minus W pump. This is W turbine in case of actual turbine. This is W pump we calculated. So rejection also you will get from here, because heat supplied we calculated 3473. Okay, so then also you will get the right answer. Let me check it. Okay, so 3473 minus this, then also you will get the same answer. Okay, 2323, close to that. Yes, very good. 2322.9, very good. मैंने कुछ डायरेक्ट यूज कर लिया, because I have not used the unit. Decimal point तक I have not used. That's why I'm getting 2323. But actually you will get 2322.9. Okay, so you will get this answer. Now the question 7 is beauty actually. Very good question, guys. Very good question. Next question, question number 7. बहुत अच्छा क्वेश्चन है बच्चों. Question number 7. What is the specific entropy generation in the boiler? What is the specific entropy generation in the boiler heat source setup? How much is the entropy generation in the boiler heat source setup? How much is the entropy generation in the boiler heat source setup? Guys, heat addition in the boiler is not reversible. Why? Because you are not adding heat at constant temperature. There is a heat addition with a finite temperature difference. That's why there are irreversibility in the boiler. Okay, and how much are the exergy destruction, how much the irreversibility, or what is the entropy generation, that also easily you can calculate. So in case of boiler, let us first focus on this entropy generation first. Entropy generation पे focus करते हैं. What is entropy generation? This question is very good, guys. Very less number of students will be able to solve this. Okay, but if you apply your mind, easily you will get the answer. Step by step approach you need to follow. So entropy generation is nothing but entropy change of system plus entropy change of what? Surrounding, or what you can say source. Because in boiler and heat source setup, there is a heat source, guys. There is a heat source. Source क्या बच्चों? Flue gases. At what temperature, guys? Flue gases are at a temperature 700 degrees Celsius. So from flue gases you are getting the heat supplied. Okay, and with that heat supplied you are producing steam. इससे हम क्या कर रहे हैं बच्चों? We are producing the steam. So this is our entire setup. This is the source and our setup is something like this. तो मैं इसको थोड़ा सा नीचे ले लेता हूं. चलिए, so this is our entire setup. This is boiler, this is water, and this is steam going. Okay, so this is our boiler. This is our boiler and source setup. Boiler and source setup. He's asking you at what rate. Okay, he is asking you what is the entropy generation. So entropy generation is nothing but entropy change of system plus surrounding. Surrounding means source, because here there is no surrounding. One is a system, boiler, in which you are converting water into steam, and second is what? Your source. Okay, so now if you want entropy generation, so entropy generation is nothing but, what is entropy change of source, guys? Source ka entropy is going to decrease or increase? For the source, entropy is going to decrease. Why? Because you are getting heat from the source, so it is minus heat supplied by temperature of the source. Are you getting the idea, guys? So entropy change of the source, change in entropy of the source is minus Qs by Ts. What is Qs? Heat supplied by the source divided by temperature of the source. What is entropy change of the system? Now I'm giving you two, okay, let me give you 10 seconds to think. Let me give you 10 seconds to think, guys, how you will write the entropy change of system. How you will write the entropy change of system. Okay, I'm giving you 10 seconds to think how you will find out the entropy change of system. So guys, for entropy change of system, this is nothing but S1 minus S4. This is nothing but S1 minus S4. How you can write this, sir? How you can write this is S4 minus S1? So guys, what is this point? What is this point? This point is 4. This is point is 2. This is 3. This is 4. This is 5. This is 6. And this is 1. So entropy change of the system means entropy change for the water is what? Entropy here at the entry to the turbine. Entropy here at the entry to the turbine. Entropy here at the entry to the boiler. So this S1 minus S4 is nothing but entropy change of the system. If you will take a boiler and a heat source setup, so S1 minus S4, this is the entropy change. From where you will get S4? S4, you know, this 3 to 4 is isentropic compression process. 3 to 4 is isentropic compression process. So S4 is nothing but S3, and S3 is nothing but SF at T condenser. S4, 3 to 4 isentropic compression, S4 equal to S3, and S3 equal to SF at TC. Okay, now if you will mark all those things here, you will get the answer. Okay, so let me mark it here. So what is S1, guys? S1 क्या लिख सकता हूं मैं? S1 from the superheated property table. This is S1. Yes or no? This is the H1. This is S1. And entropy at the entry to the turbine. This is S1. 7.2588. What is S4? S4 equal to S3 and S3 equal to SF at T condenser. So this is this. SF at T condenser. So this is this 0.6386. 0.6386. 0.6386. How much is the heat supplied, guys? That we already calculated. How much heat you are supplying? That is 3473 kilojoule per kg. This is the heat we are supplying. Okay, this is the heat we are supplying. Minus 3473 divided by temperature of the source. And you know, guys, temperature we need to take in Kelvin. So this is 700 plus 273. So if you solve all those things, you will get the entropy generation. You will get the entropy generation, guys. Very simple question. Only you need to follow the basic step, basic process. जयराम का आंसर बिल्कुल सही है. अच्छा, प्रसाद का आंसर बिल्कुल सही है. प्रसाद, your answer is right. प्रसाद जोशी. Jairam, your answer is not right. You need to check it again. 2 point is not the right answer. I think 3.5. Let me check. 3.5 or what I will get. I don't remember this time. Let me check. Okay. So 3473 divided by 700 plus 273. So this is 3.56. Let me write it here. So So minus 3.5693 plus this data 7.2588 minus 0.6386. .6202 minus 3.5693. So you will get 3.05. This is the right answer, guys. 3.0509 kilojoule per kg Kelvin. This is the entropy generation. Entropy generation is nothing but 3.05. I don't know where you are making the mistake, but I got two answers. दो answers मिले मेरे को, एक तो 2 point something and another one is 3.59. Both are wrong actually. Prashad, please check your calculation. 3.59 is not right actually. This is not right. If you are getting 3.59, this is wrong. ये भी गलत है, and this is also wrong. The right answer is 3.051. 3.051 kilojoule per kg Kelvin. This is the entropy generation, rate of entropy generation. Okay, not rate. This is the entropy generation actually. Kilojoule per kg Kelvin. This is the entropy generation in this process. In case of boiler and source setup. I hope these 7 questions are clear to you. So, and you got some basic idea about the Rankine cycle, how to calculate all those things like the cycle efficiency, how to calculate the isentropic efficiency of the turbine. Okay, how to calculate the net work, how to calculate turbine work, all those things. Let us now move to some more important questions, guys. So this is question number 8 in front of you. Again, it is from the NPTEL assignment, guys. Question number 8 from the NPTEL assignment. A steam power plant operating on a simple Rankine cycle has a boiler and condenser pressure of 3 megapascal and 10 kilopascal. So this is boiler pressure PB, this is condenser pressure PC. Okay. If the steam leaves the boiler as saturated vapor, guys, it is very clearly mentioned the steam which is leaving from the boiler as what? Saturated vapor. So this is not superheated cycle. Okay, so in this case, because in most of the NPTEL assignment, you're not going to find out these kind of data table. So I picked all this data from the steam table only, and I provided you here. Okay, because in GATE paper, if you will get some kind of question, surely you will find some kind of data also. But in NPTEL assignment, they expect the student is going to refer those kind of steam table, and then he will solve those questions. So these data table I am providing you. Okay, in actual assignments there is no such data table, so you need to refer to the steam table. But for GATE, you need not to worry about steam table, how to read steam table. Okay, that is not required. But for conventional paper, conventional university paper, you need to know like how to actually read that steam table. Okay, so clearly, like here, if you will draw the Rankine cycle, something like this. Now it is given the steam which is leaving to the boiler is saturated vapor. So this is the steam which is leaving to the boiler. So this is the expansion, isentropic expansion. This is the condenser exit, something like this. This is pumping process, isentropic expansion, compression, pumping process, and then the process will be something like this. So the cycle will look like something like this. Point 1, point 2, 3, 4, 5. Again, this is TS diagram. TS diagram. So as it is given in this question, the entry to the turbine is what? Saturated vapor. So I'm taking this point on the saturated vapor line. What is asking you? What is the thermal efficiency of the cycle? Now directly you are getting the question, what is the thermal efficiency? What is the thermal efficiency? So guys, please try to solve this. I'm giving you some time. Please try. Can we take from temperature and pressure term? What do you want to take, Jaram? Your question is not clear. So what do you want to take from the pressure and temperature term? Okay, so let me solve it for you guys. So thermal efficiency is nothing but W net divided by heat supplied. So W net is nothing but W turbine minus W pump divided by heat supplied. Okay, so let us solve all those things one by one. So what is W turbine, guys? W turbine is nothing but H1 minus H2. So what is H1? H1 is HF at boiler pressure. Where this point is, guys? This point in the saturated vapor line at boiler pressure. So this is nothing but Hg at boiler pressure. So at boiler pressure, Hg 2803.2. Let me zoom it for you guys. So 2803.2. 2803.2. This is the enthalpy at the turbine inlet, because this is Hg. Hg, enthalpy of the saturated vapor at the turbine inlet. So let me write it here, 2803.2. What is H2? H2 we don't know. H2 0.2 lies in the wet region. 0.2 lies in the wet region. So we can write this H2 as, H2 को हम कैसे लिख सकते हैं? H2 equal to HF plus X HFG. What is HF? At condenser pressure, what is HF? This is at condenser pressure 191.81. 191.81 plus X into HFG. What is HFG? At condenser pressure, this is 2392.1. 23921. Okay, but for solving this, we need to find out first X. What is the dryness friction at the exit of the turbine? What is the dryness friction at the exit of the turbine, guys? And for calculating this, you need to equate S1 equal to S2. आपको क्या इक्वेट करना पड़ेगा? You need to equate S1 equal to S2. What is S1? S1 is Sg at boiler pressure. Boiler pressure, what is Sg? 6.1856. Boiler pressure 3 megapascal. This is Sg 6.1856. What is S2? S2 point lies in the wet region, so this is nothing but SF at the condenser pressure. SF 0.64920 SF plus X into SFG. X into SFG. What is SFG? At condenser pressure 7.4996. 7.4996. Okay, I hope all these data are available, visible to you. So 7.4996. If you will solve, you will get the X. Let me solve it for you guys. So 6.1856 minus 0.64920 divided by 7.4996. You will get X equal to 0.7382. 0.73822. This is a dryness friction at the exit of the turbine. Dryness friction at the exit of the turbine, X. Now let us put this value X here. X को यहाँ put कर देते हैं, so that we will get the H2. 2392.1 plus 191.81. You will get H2 1957.72 kilojoule per kg. So this is H2. This is H2. Okay. So now what is the turbine work? Turbine work क्या आ जाएगा? This will be 2803.2 minus H2. So you will get turbine work close to 847. 845.47 kilojoule per kg. .4748 kilojoule per kg. Okay. Now what is pump work, guys? Pump work क्या हो जाएगा? What is pump work? WP is nothing but H4 minus H3. Okay, this is H4 minus H3, or this is nothing but VDP. Okay, so I can write it as V3 specific volume, because you know liquids are incompressible. Liquids are incompressible. Generally, we treat this process like the volume is not going to change much. for the liquids. So this is V3, specific volume for the liquid, saturated liquid at the entry to the pump. So this is V3 into the change in pressure, and the change in pressure means the boiler pressure minus condenser pressure. So what is V3, guys? What is V3? V3 you can easily get from this at 0.1 0.01 megapascal or 10 kilopascal. This is Vf. If you refer to this diagram, this particular table, 0.0010127. Okay, so let us use this data. Zero point zero zero one zero one 027. Boiler pressure is what? 3 megapascal. So this is 3000 minus 10. Although you can neglect this, guys, because this term is going to come out very less. बहुत कम term आएगी. 3.0207 kilojoule per kg. You can neglect, okay, because if you will neglect, then also you will get the answer. 3.0207. So now what is W net, guys? W net will be W turbine 845.47 minus 3.0207. You will get 842.4493 kilojoule per kg. 842.4493. This is W net. Okay, what is heat supplied, guys? Heat supplied is nothing but H1 minus H4. H1 minus H4. What is H1? H1 already we calculated. Please check. H1 we calculated. H1 is what? H1 is this 2. We from the data table only we find out this value 2803.2. Okay, 2803.08. Let me check. 2803.2. What is H4, guys? H4, I can write it here. H4 equal to H3 plus WP. H4 minus H3 is WP. The change in enthalpy at the exit of the pump minus enthalpy at the inlet of the pump, that is pump work. So H4 minus H3 is WP. So H4 equal to H3 plus WP. Okay. So WP already we calculated. It is something 3.0207. H3 is nothing but HF at condenser pressure. HF at condenser pressure. So what is HF at condenser pressure? This is HF at condenser pressure 191.81. 191.81 HF at condenser pressure. HF at condenser pressure. So 191.81. So let me put it, all those things. 191.81 plus 3.0207. You will get H4 equal to 194.8307 kilojoule per kg. If you will subtract it from this 2803.2 minus this, you will get heat supplied. Heat supplied you will get, because this we calculated, heat supplied you will get 2608.3693 kilojoule per kg. Okay, now we are having W net also, we are having heat supplied also, and if you will take their ratio, you will get the answer 842.4493 multiply by 100, and exactly you will get 32.29, something like that. 32.29. Very good, Naga. So 32.29. Let us see. Yes, so the range given for this question, guys, because this question was from NPTEL assignment, if you're getting the answer in the range 31.5 to 33.7. Okay, so we got the answer. We got the answer exactly in between this. We got the answer 32.29%. And if you are getting the answer in this range 31.5 to 33.7, then also your answer is right. Okay, let me mark it here also, guys. So from this data, thermal efficiency is nothing but W net by heat supplied. So this is nothing but 842.4493 divided by heat supplied. Heat supplied is this 2608.3693. Multiply by 100, you will get this efficiency 32.2979%. I hope you all are getting this answer, guys. Okay, very good. So easy question, slightly lengthy. Okay, but questions are very easy. So I think this is clear to you how to find out the cycle efficiency. Please check it again, guys. So I discussed with you this particular question. Question you will get, guys, if you registered on YourPedia, some Google form. If you filled, you are going to get all those questions. Other than these 25 questions, you will get a set of 100 questions. Okay, actually you will get a set of 109 question, and out of those 109 question, 100 questions are very much relevant for GATE examination. Okay, so don't worry, you are going to get that file, okay, on your email if you registered on YP panel. If you filled that Google form, not registered, okay, I don't know you filled or not, but if you filled, you surely you will get that file on your email. Question number 9, guys. Question number 9 in front of you. A power plant produces 25 kg steam at 3 megapascal 600 degrees Celsius. So 3 megapascal पे at 3 megapascal 600 degree Celsius means you are having the superheated steam. आपके पास क्या है? Superheated steam. Although he can give you this data also. यहाँ पे 3 megapascal पे he can give you this data also. Okay, and from that also you will get the idea कि this point lies in the superheated region. Reheating is done. You carried out the reheating at 500 kilopascal. Now we are going to solve questions related to reheating. Till the steam pressure rises to 400 degrees Celsius and subsequently the steam is expanded in the low pressure turbine. The condenser temperature is 45 degrees Celsius. Then what is the net work output from this cycle? Correct to 1 decimal place. Very good question, guys. बहुत अच्छा क्वेश्चन है. Now we are moving to slightly different question. First 15 questions are numerical based. They are going to take some time. Last 10 questions we will be easily able to complete in half an hour because all are direct one liner only. Okay, so I have chosen those 25 questions. Okay, out of those 25, 15 are numerical based and 10 questions are direct one marks question. So chaliye, let me draw first the cycle. So the cycle will be something like this. Temperature, entropy, this is a cycle, something like this. Now you're having the steam at this temperature, this pressure, 3 megapascal, 1600 degrees Celsius. So this is expanding and again reheated. इसको आपने क्या कर दिया? Reheat कर दिया. This is the reheated. So this condition is what? 400 degrees Celsius. Pressure 500 kilopascal. Pressure 500 kilopascal. This condition, guys, this particular condition, okay, this particular condition is 600 degrees Celsius. Pressure 3 megapascal. Okay, after reheating, this is again expanded. So this is the heat rejection in the condenser, something like this. So the cycle will be something like this, guys. This is our critical point. Okay, so this is our reheat pressure. ये कौन सा pressure है बच्चों? This pressure line is what? This is representing reheat pressure. Okay, this is representing the reheat pressure. Let me zoom it for you guys. Something like this. Let me mark here different points. So this is 1 to 2. Suppose this point is 1, this point is 1. 1 to 2 is the expansion in the high pressure turbine. 1 to 2 is the expansion in the high pressure turbine. 2 to 3 is the heat addition in the reheater. Okay, so this is reheating process. 2 to 3 is the reheating process. 3 to 4 is the expansion in the low pressure turbine. 3 to 4 heat work expansion, expansion of the steam in the low pressure turbine. 4 to 5 heat rejection in the condenser. 5 to 6 isentropic compression या pumping process. 6 to 7 heat addition in the economizer. 7 to 8 heat addition in the evaporator. 8 to 1 heat addition in the superheater. So 8 to 1 superheating, 1 to 2 expansion in high pressure turbine, 2 to 3 reheating. 3 to 4 is expansion in the low pressure turbine. This is rejection in the condenser, and this is your isentropic compression process. Heat addition in the economizer, heat addition in the evaporator, and then you are having superheating process. So the boiler pressure is given to us 3 megapascal and 600 degrees Celsius. The reheat temperature is given to us 400 degrees Celsius, 500 kilopascal. Okay. This temperature, the condenser temperature is 45 degrees Celsius. The condenser temperature is 45 degrees Celsius. So the steam produced, how much steam produced? 25 kg per second. He's asking you what is the net work output. What is the net work output? So guys, this question is very easy. Because if you want a net work output, let me mark it here. The net work output, W net, is nothing but WT1 plus WT2. The work of the high pressure turbine plus work of the low pressure turbine minus WP pump work. That is going to give you W net. He's asking you W net. Yes, net work output from the cycle. What is the net work output of the cycle? So here, because in reheating case, we use two turbine, high pressure turbine, low pressure turbine. So the work divided by high pressure turbine, work divided by low pressure turbine minus pump work, that is going to give us W net out. Net work out. So what is WT1, guys? WT1 is nothing but H1 minus H2. What is WT2? WT2 is nothing but H3 minus H4. And WP, specific term, if I will write all those things on the specific term, WP is nothing but H6 minus H5. The enthalpy, specific enthalpy at the exit of the pump minus specific enthalpy at the inlet of the pump. Okay. Now what is H1, guys? What is H1? H1 is the enthalpy of the superheated steam. Where this point lies, guys? This point lies in the superheated region. So at 3 megapascal, 600 degrees Celsius, this is the enthalpy. So this is H1. Enthalpy of the superheated steam at the entry of the turbine, high pressure turbine. So this is 3682.8. What is H2? H2 again point lies in the superheated region. How you can say? Because sir, at this point entropies are going to remain same. देखो ये कुछ गलत हो गया है. This will be 7.495, something like this. Almost close, because at this pressure, this temperature, this expansion is what? Isentropic expansion. So S1 is equal to S2. S1, this is S1 is equal to S2. S1 equal to S2. So if you will check it here, अगर आप इस टेबल में चेक करोगे, in this particular table, if you will check 0.5 pascal पे, 0.5 megapascal पे, because I checked that particular table, you will not find entropy Hg. Like if you will check at this pressure 0.5 megapascal, if you will check this saturated water and steam table, you will not get entropy close to 7.49. Okay, Sg will be slightly less than that. Okay, and if you're getting Sg less than that, it means clearly you can get the idea that this point also lies in the superheated region. So in the superheated region, what is the entropy? These two are almost same, guys. 7.51, 7.49. So means this is the point where you are going to get at the turbine exit, high pressure turbine. So this is H2. Okay, this enthalpy 3272. This is H1. This is H2. 3272.3. So let me mark it here. 3272.3. plus. Again, what is H3? Okay, अच्छा ये पॉइंट आ गया, देखो this we are having 2 points, हमारे पास 2 points है बच्चों, we are having 2 points. Okay, this is one point and this is another point. Okay, I think yes, so these are the 2 points. So this is the point 400 degrees Celsius, 500 kilopascal. 400 degrees Celsius, 500 kilopascal. This is H3 guys, not H2. This is H3. मेरे ख्याल से इसमें हमने एक टेबल में डेटा मिस कर दिया है. So this is H2. This is H3. Okay. This is H3, not H2. Okay. This is H3. H2. This is not H2. Okay. This is H3 guys. Okay. So let me mark it here H2 only. H2 plus H3. Okay. What is H3? H3 is this. 3272 at this pressure, reheat pressure 500 kilopascal, reheat temperature 400 degrees Celsius. This is enthalpy 3272.3. 3273. 3272.3 minus H4. What is H4? H4 is the point lies in the wet region. Okay, H4. So this is H4 minus H6 minus H5. H6 minus H5. H6 minus H5. What is H5? H5 is HF. HF at condenser pressure. So this is HF at condenser pressure 188.13. 188.43 at condenser pressure. This is HF. You can check 188.43 HF at condenser pressure. So let me put it here. 188.43. Okay. H6 also you are going to get. H6 कहां से आएगा बच्चों? Let me mark it here so that you will get the idea. H6 you will get. You know, WP is nothing but again V dP. V is the specific volume of the liquid at the entry of the pump. dP is the boiler pressure minus condenser pressure. Both are given to us. Both we know. Boiler pressure is 3 megapascal and the condenser pressure is at 45 degrees Celsius. This is condenser pressure. Close to 9.59 kilopascal. 9.59 kilopascal. This is our condenser pressure. So we know both. So easily you will be able to calculate the pump work. यहाँ से आपका क्या आ जाएगा? Pump work आ जाएगा. And if you will want H6, so H6 is nothing but H5 plus WP. H5 plus WP. H5 we know this is 188.46, and if you will add pump work in this, you will get H6. Okay, so easily you will be able to calculate all those things. ये आपका पास आ जाएगा. You will get this and this. Okay, actually at this 5 megapascal, 0.5 megapascal, in actually we missed one table. तो यहाँ पे दो टेबल होनी चाहिए थी. 0.5 megapascal, 0.5 megapascal, one table at a temperature 400 degrees Celsius and another table at a temperature close to 310 degrees Celsius. Okay, why? Actually, how I can say that? How I can say that? Because at 310, at a temperature, let me use here the property table, guys. Okay, so I'm having steam table with me. In IIT Bombay ka steam table hai ye, and let me use here the superheated steam table for the pressure 0.5. So let me take it here, the 0.5 megapascal. Okay, 0.5, yes, 500 kilopascal or 0.5 megapascal. So I'm having this table. Okay, so at this temperature, if you want entropy close to 7.49, let me do it for you guys. Okay, so at this temperature, at this pressure, 0.5 megapascal, if you want entropy, this अपने को क्या चाहिए? S1 equal to S2. Okay, S1 equal to S2. So if you want entropy, this 7.5103, if you will check, you will find it close to 310 degrees Celsius. So at 310, you will find this property. Okay, for the pressure 0.5 megapascal, okay, you will get this entropy close to this at a temperature 310 degrees Celsius. Okay, and at that temperature the enthalpy is 3085.2. So let me directly write it here. so that we will at least get the answer. तो मैं यहाँ सीधा लिख देता हूँ. Let me write it here directly. H2 you can take from the steam table is 3085.2 kilojoule per kg. So H2 you can directly take 3085.2 kilojoule per kg. Are you getting the idea, guys? So I'm using this steam table, and from that steam table only I am writing this data. Okay, but for GATE examination you are going to get this, don't worry. Okay. चलिए. So let us now put all these values. So this is also, now we know 3085.2. Okay. H4, what is H4? H4 कहां से आएगा बच्चों? From where you will get H4? For H4 you need to equate S3 and S4. You need to equate S3 and S4. Okay, guys, this process 3 to 4 is isentropic expansion process. So what is S3? S3 is the entropy in the superheated region at a pressure 0.5 kilopascal, 0.5 megapascal. So 500 kilopascal pe what is the entropy? It is 7.7955. 7.7955. Okay, this is the entropy. So this is S3. So let me write it here, 7.7955. 7.7955. What is S4? That we can write it as SF plus X SFG at condenser pressure. SF plus SFG at condenser pressure. So what is SF at condenser pressure? SF is this 0.63861 plus X. SFG is 7.5247. And this is 7.7955. So let us solve for finding out the dryness fraction at the exit of the low pressure turbine. What is the dryness fraction at the exit of low pressure turbine? So 7.7955 minus 0.63861 divided by 7.5247, you will get 95%. Dryness fraction x equal to 95%. या इसको मैं लिख देता हूं फ्रैक्शन में 0.9511. 0.9511. So now easily you will be able to find out H4. H4 को आप easily आप निकाल पाओगे now. How? You know H4 equal to HF. What is HF? At condenser pressure 188.43. This is HF. So 188.43. HF at the condenser pressure plus dryness fraction 0.9511 into HFG. So at condenser pressure, what is HFG? It is 2394. 2394. So you will get this answer 2394 plus 188.43. You will get 2465. 2465.41 kilojoule per kg. Okay, 2394 multiply by 0.9511 plus 188.43. I'm getting 2465.41. Okay, 41 या 36 कुछ भी इसके आसपास आ जाएगा. Okay, now let us put this value here also here. So H4 we got 2465.36. 3641 जो भी आया था मैं 41 ही लिख देता हूं 41. So we know this also we calculated, this also we know, this also we know. H6 is H5 plus WP. So what is H5? It is 188.43 plus WP. WP is nothing but V into boiler pressure minus condenser pressure. What is V? How much specific volume that pump is handling? That is equal to VF at condenser pressure. VF at condenser pressure. What is VF at condenser pressure, guys? If you will observe it here, this is VF at condenser pressure, 0.00100992. This is the volume the pump is handling. So let us put this data here. 0.001000992 into boiler pressure 3 megapascal minus condenser pressure is 9.59. Okay, 3 minus 9.59. Okay, 9.59. Let me check, because in kilopascal I'm writing this is 9.59 kilopascal and the boiler pressure is 3000 kilopascal. 3000 kilopascal. So let us solve this. 3000 minus 9.595 multiply by 0.001000992, you will get 3.02. Okay, 3.02. This term, the pump work, the WP will come out 3.02 kilojoule per kg. This is the pump work you are going to get. The pump work you are going to get this. Okay, and if you add in this 188.43, you will get 191. The H6 will be 191.45 kilojoule per kg. This is the enthalpy at the exit of the pump. So now guys, we are having all these data. So W net will be this minus this plus this minus this minus H6 is this. Okay, minus this. Okay, so let me solve it for you. 3682.8 minus 3085 minus 0.2 plus 3272.3 minus 2465.41 minus 3.02. So you will get 1401. 1401.47 kilojoule per kg. This is W net I am getting. Okay, this is W net I am getting. 1401.47. This is W net, kilojoule per kg. This is W net. But what we want, guys? We want W net in megawatt. हमें किसमें चाहिए? Megawatt में. It means we need to multiply by with mass of the stream. How much is the mass of stream, guys? 25. So 25. Let me multiply with this. So let me multiply with this 25. You will get 35036.75. You will get this in kilojoule per second. This you will get in kilojoule per second. Why? Because this is the mass of steam in kg per second. How much is the mass of steam we are circulating, guys? This is given to us here. You can check. You need to aware about what he's asking you. He's asking you the work in megawatt, guys. Please check this. He's not asking you specific work, kilojoule per kg. He's not asking you specific work. He's asking you the work in megawatt. So you need to multiply with this mass of the steam, 25 kg per second. Okay. So if you multiply with this, you will get the answer. And I hope most of you are getting this answer. So this is in kilowatt. So in megawatt, you can write it as 35.036 megawatt. So this is W net in megawatt. W net in megawatt. 35.036. So let us check what is the range given for this question, guys. So the exact range which is given for this question is 35.5 to 35.1. Very close, but we are getting in this range. Okay, so we are getting the answer in this range only. So our answer is right. 34.5 to 35.1. So our answer is right. Slightly lengthy question, guys, but very good question. With this, you will get the idea how to calculate the net work in case of reheat cycle. So for reheat cycle, first you need to calculate the work for the high pressure turbine. You need to calculate the work for the low pressure turbine. You need to add both these two. You will get the net work. And second most important thing, guys, you need to check what he's asking you. He's asking you the specific work. in kilojoule per kg, or he is asking you the work in megawatt. In this case, he asked you the work in megawatt, means we need to multiply with this. This data is very much relevant for us, very much useful for us. So 25 kg is the mass of steam produced. So 25 multiply by this, then only you are going to get the answer. Okay, I hope you all are getting this answer. Okay, chaliye, let us now move to next question. Question number 10. Question number 10. Ideal Rankine cycle with a boiler pressure 3 megapascal. Maximum and minimum cycle are this. So this is the maximum temperature. This is the maximum temperature, 450 degrees Celsius. This is minimum temperature, means condenser temperature. If a Carnot cycle is also allowed to operate within the same temperature limit, then what is the ratio of the thermal efficiency of the Rankine cycle with the Carnot cycle? He is asking you the ratio of the thermal efficiency of Carnot. Yeah, efficiency of Carnot, okay, divide by thermal efficiency Rankine. So this is the question. What is the ratio of the efficiency of the Carnot cycle? If Carnot cycle is also allowed to operate between this temperature range, so what will be the ratio? So guys, you know, Carnot efficiency depends on the temperature limit only. So this is nothing but 1 minus T lower by T higher. So this you can write it as 1 minus T lower is 45 plus 273. T higher is 450 plus 273. So from this you will get the Carnot efficiency. इसको सोल्व करोगे तो you will get the Carnot efficiency. Okay, 45 plus 273 divide by 450 plus 273, 1 minus, you will get 56%, means 0.56, 0165. This is the efficiency. In fraction I am writing. So in fraction you are going to get 0.560165. This is the Carnot efficiency. Now if you will find out the Rankine efficiency, easily you will get this ratio. Easily you will get this ratio. So now guys, at this pressure, boiler pressure is 3 megapascal. So at 3 megapascal, if you will check, what is the saturation temperature? At 3 megapascal, if you will check, the saturation temperature is 233.853. 3 megapascal boiler pressure, the saturation temperature is 233.853. It means the steam which you are producing at 450 degrees Celsius, this is the superheated steam. Superheated steam. Are you getting the idea, guys? So just by observing this property table, you can conclude that the boiler pressure is 3 megapascal. At this boiler pressure, this is the temperature, T saturation 233.853. And at this temperature, the 450 degrees Celsius, the maximum temperature is more than this, means we are getting the superheated steam. It means for writing the H1, enthalpy at the entry of the turbine, directly you can write from this property table, 3 megapascal, 450 degrees Celsius. This is the enthalpy, sorry. This is the enthalpy at the entry of the turbine. So H1, you can write it as 3344.8 kilojoule per kg. Are you getting the idea, guys? Okay. What is S1? Let me now solve this without drawing that cycle, so that you will also get some more exposure. So S1 is nothing but S1 is the point entry to the turbine. So at point 1, entropy is 7.08. 7.0856. So this is equal to S2. This is equal to S2. Yes or no? And S2 will lie in what? S2 point will lie in the wet region. Okay. So S2 equal to SF at condenser pressure. So this is the condenser temperature. This is the condenser pressure. So at condenser pressure, what is SF? It is 0.63, 0.63861 plus X into SFG. So SFG is 7.5247. 7.5247. 7.5247. So if you will solve this, guys, you will get X. Dryness friction आ जाएगा आपका turbine के exit पे. You will get the dryness friction at the exit of the turbine. So 7.08, 56 minus 0.63861 divided by 7.5247. you will get x equal to 85%, means 0.8567. This is the dryness fraction you are going to get at the turbine exit. Dryness fraction at the turbine exit. Very simple. Now what is H2, guys? What is H2? What is H2? So can I write this H2 equal to HF? What is HF? At condenser pressure, this is HF 188.43. So 188.43 HF plus X. What is X? X is this, we obtained 0.8567 into HFG. Where? At condenser pressure, guys. This 0.2 lies in the wet region at condenser pressure. So at condenser pressure, this is HF, this is HFG 2394. 2394. So let us solve this. 2394 plus 188.43, you will get 2394 multiplied by 0.8567 plus 188.43, you will get 2239.3698 kilojoule per kg. So this is enthalpy at the turbine exit. Enthalpy at the turbine exit. So what is W net, guys? W net also easily you will be able to write. W turbine will be H1 minus H2. So it is nothing but 3344.8 minus 2239.3698. So you will get W turbine. You will get W turbine 1105.43 kilojoule per kg. This is turbine work. This is turbine work, guys. You are going to get 1105.43. Guys, the right range for this question is 0.61 to 0.63. Naga, your answer is wrong. The right answer for this question is 0.61 to 0.63. Please check. Okay. So let us find out W pump also, guys. What is W pump? Pump work. So WP, pump work, is nothing but V into boiler pressure minus condenser pressure. So V is what? It is V entry, specific volume for the liquid at the pump inlet. So that is nothing but VF at condenser pressure. So this is 0.VF at condenser pressure. Guys, this V always will be VF at the condenser pressure. So what is VF at the condenser pressure? This is VF at condenser pressure, 0.001000992 into boiler pressure. What is the boiler pressure? It is 3 megapascal. So 3000 minus what is condenser pressure? Condenser pressure is 9.5995. Okay. I think earlier also we got the similar kind of data. So Acha, you are telling about dryness fraction. Good. Dryness fraction is in that range only, Naga. Dryness fraction is right. If you are getting dryness fraction, that is right. So let us solve this. 3000 minus 9.5995 multiplied by 0.001000992. I hope you will get 3.02. You will get pump work 3.02 kilojoule per kg. So this is WP you are going to get. This is WP you are going to get. Okay. So what is H4? What is H4? Enthalpy at the boiler inlet. H4. That is nothing but H3 plus WP. What is H3? H3 is HF at condenser pressure. What is HF at condenser pressure? 188.43. So 188.43 plus WP. What is WP? 3.02. So you will get enthalpy at the boiler inlet. Enthalpy at the boiler inlet. 188.43. You will get 191.45 kilojoule per kg. 191.45 kilojoule per kg. Now let us put all the data and you will get the Rankine efficiency. Efficiency of the Rankine cycle. So let me write it here. मैं यहाँ लिख देता हूँ. Efficiency of Rankine cycle. Thermal efficiency of Rankine cycle. So this is nothing but W net, W turbine minus W pump divided by heat supplied. So this is nothing but W turbine. How much is the W turbine, guys? That is H1 minus H2. That is 1105. Let me write it here. 11. Let me write it here. 1105.43. What is W pump? That is 3.02. How much is the heat supplied, guys? That is nothing but H1 minus H4. H1 minus H4 is heat supplied. H1 minus H4. What is H1? H1 is the enthalpy at the boiler exit or enthalpy at the turbine inlet. What is H4? H4 is the enthalpy at the boiler inlet. So this is H4. This is H4, 191.45. Okay, and what is H1, guys? H1 is this 3344.8. Enthalpy for the superheated steam. Why? Because the entry to the turbine is superheated steam. Entry to the turbine is superheated steam. So this is the enthalpy of the superheated steam. Okay, 3344.8. So let me put it here. 3344.8. 3344.8 minus H4. H4 is nothing but 191.45. So let me put all this data. 1105.43 minus 3.02. And let us check we are getting the answer in the range or not. 1105.43 minus 3.02 divided by 3344.8 minus 191.45. So you will get 34. This Rankine cycle efficiency, Rankine cycle efficiency, efficiency of Rankine cycle, you will get 0.34. 0.3495. Okay, 0.3495. This is the efficiency of the Rankine cycle. But what he asked you guys in this question, he asked you the efficiency of the ratio of the efficiency of Carnot cycle and the efficiency of the Rankine cycle. What is the ratio of the efficiency of Carnot and Rankine? Okay, actually not Carnot by Rankine. He asked you that because Carnot efficiency will be more. Okay, so he asked you the efficiency ratio, the efficiency of the Rankine, thermal efficiency of the Rankine by the thermal efficiency of the Carnot. This ratio he asked you. So what is this ratio, guys? Efficiency of the Rankine divided by efficiency of Carnot. How much is the Rankine cycle efficiency? It is 0.3495 we got, and this we are getting 0.560165. So if you will divide, you will get this ratio. 0.3495 if you will divide by this, 0.3495 if you will divide by 0.560165, you will get 0.6239. You will get a 0.3269. So guys, this is the Rankine efficiency we got, and this is the Carnot efficiency, guys. What is Carnot efficiency? 1 minus T lower by T higher. So T lower is what? It is a condensation temperature. All temperature you need to put in Kelvin scale. So 45 degrees Celsius, 450 degrees Celsius, you will get the Carnot efficiency. So this we calculated, okay, initially only. So this is Carnot efficiency, and now we calculated the Rankine efficiency also. Okay, this is the Rankine efficiency, guys, we calculated. I hope you are following the entire question. Slightly lengthy question. These questions are slightly lengthy, but these are very easy actually. So this is the Rankine efficiency, 0.3495. Okay, and we got this ratio 0.6239. Let us see what is the range given. Yes, the range is 0.61263. The range for this question is 0.61 to 0.63. This is the range, and exactly we are getting the mid of this, 0.6239. This is the ratio we are getting. Means our answer is right. Very good. Okay, so in this question he asked you about the ratio. Yes, Vijay Raju, very good. Naga, your answer is also right, 0.62. Very good, guys. तो थोड़े lengthy question है, but if you will practice, you will find this question very easy. So I hope you all are getting the answer in this range. Let us now move to next question, guys. Question number 11. This is question number 11, guys. This is question number 11. In a steam power plant, the saturated vapor is at 5 megapascal, leaves the boiler and then superheated to 600 degrees Celsius in an external superheater. So there is a Rankine cycle and you are producing the superheated steam. During the expansion through a turbine, some amount of steam is extracted at the pressure of 0.4 megapascal. So this question is actually related to regeneration, guys. This question is related to regeneration. बहुत अच्छा क्वेश्चन होने वाला है बच्चों. Regeneration. So we discussed some question related to superheating, then we discussed some question related to reheating, and now you are having another question related to regeneration. You will find this question lengthy. Okay, अभी देख के ही बच्चों को लगेगा सर इतना डेटा. Okay, and you will feel some kind of कि sir how to solve these kind of questions. Okay, so much data, but don't worry. Like if you follow the step-by-step approach, you will find this question very easy. So regeneration say, like earlier also some question were asked in the GATE examination. So that concept is important for us. We need to know about what is regeneration. Okay. And how to write the energy balance for the regeneration process. So what is saying, guys, this is a steam in boiler. You are producing steam at 5 megapascal, this temperature, and then steam is, expanded into the turbine. Okay. Some steam is extracted from the turbine. Okay. Regeneration you are carrying out at a pressure 0.4 megapascal is supplied to open feed heater. So there is an open feed heater in which you are taking the steam from the turbine and simply you are mixing that steam into the water. There are two type of feed water heater. One is open type. In open type, directly we mix the steam taken by the turbine into the feed water, and there are closed type feed water heater also. In closed type feed water heater, we use some kind of shell and tube type heat exchanger. Okay, and in those we use the heat of the steam coming out from the turbine to heat the feed water, just to increase the mean temperature of heat addition, so that more will be the mean temperature of heat addition, less will be the temperature difference between the flue gases and the temperature of the water. And if the less is the temperature difference between the water and the flue gases, the less will be the irreversibility and more will be the efficiency. So guys, if you want more efficiency, we need to increase the mean temperature of heat addition. So by superheating we can increase the mean temperature of heat addition, but superheating से क्या होता है? Superheating is having limit. Superheating we cannot carry out beyond a certain limit because there is a particular metallurgical limit. Because when you are carrying out the superheating, the temperature is increasing. So with superheating, the temperature increases, but due to the metallurgical limit, we cannot go beyond a certain value. So there is a limit of increasing the mean temperature of heat addition with superheating. Regeneration also, but with superheating, if you further want to improve the quality of the steam, okay, or further if you want to improve the mean temperature of heat addition, we use different types. We use actually these things in combination: superheating, regeneration, reheating. Okay, so regeneration we are carrying out open feed water heater. Directly the steam which we are taking from the turbine, we are mixing it into the feed water. The condition at the exit of the feed water is saturated liquid at the constant pressure. The condenser pressure is this. The net power output of the cycle is 1 megawatt. The net power output of the cycle is 1 megawatt. Then what is the amount of heat added to the steam in external superheater? How much is the steam added in the external superheater in kilowatt? So let me draw the cycle, guys, cycle diagram, because if you are able to draw the cycle diagram, then you will find this question very easy. So guys, this cycle is something like this. Let me draw here the TS diagram. So this is temperature versus entropy diagram, something like this. So first you are having the steam at a pressure 5 megapascal, temperature 600 degrees Celsius. So you are having steam at this condition. So this is the steam. 600 degrees Celsius, 5 megapascal. You are expanding the steam. But expand करते करते आपने क्या किया? Some part of the steam you have taken. Some part of the steam you have taken from this, and you mixed this steam into the open feed water heater. Okay, and further there is expansion also. Expansion is taking place something like this. So this is the exit, and then this is the heat rejection in the condenser, something like this. This is your pumping process. This is your pumping process. This is the raise in energy, because this is the water water which is coming out from the pump, that water is directly taking heat from the steam coming out from the steam turbine, and you will get the enthalpy somewhere here. Why? Because it is mentioned at the exit of the feed water heater you are getting the saturated liquid. So this is the exit condition. Okay, and again if you will pump it something like this, you will have the cycle, complete cycle diagram, something like this. So the cycle diagram will be something like this. So this is the cycle, Rankine cycle with regeneration. This is Rankine cycle with regeneration. Let me mark it here, the various points. This is point 1, guys. This is entry to the turbine or exit of the boiler. This point 2, from this point 2, guys, you are taking some part of the stream. Suppose you are taking M fraction. M is representing the fraction of the stream which you are taking out from the steam turbine. So M is the fraction of the steam which you are taking. Okay. So remaining mass will be what? That will be 1 minus M. Remaining fraction will be 1 minus M. So 1 is representing the total fraction. M is representing the fraction of the stream which we are taking from the steam turbine. Okay. At this pressure, guys, what is this pressure? This pressure is actually given to us. ये pressure अपने को given था. ये वाली line में लिख देता हूँ. This pressure is given to us. I think this is 0.4 megapascal. 0.4 megapascal. Okay. So this pressure is 0.4 megapascal. This line represents 0.4 megapascal. This is your condenser temperature, guys, and the condenser temperature is what? What is the condenser temperature? Condenser temperature is given to us 7.5 kilopascal. 7.5 kilopascal is the condenser temperature. So this is 7.5 kilopascal condenser temperature. तो मैं इसको नहीं लिखता because at 7.5 kilopascal temperature, what is temperature? Temperature is this 40.29 saturation temperature. So this is 40.29 degrees Celsius because we are having the temperature versus entropy line. So it is good to write it here temperature, not pressure. Okay. So although this line is representing constant pressure, constant temperature, phase change. So now the net work output of the plant is given to us. The net work output is 1 megawatt. 1 megawatt. He is asking you how much is the heat added in the external superheater. How much is the heat added in the external superheater? So let me write here all the points. This is 1, this is 2, this is 0.3, this is 0.4, this is 0.5, 6, 7, 8, and this is point is 9. This point is 9, guys. And this is the reheating process. This is the superheating process. This process is the superheating process. Yes or no? This point is the superheating process. So what is asking you actually? He is asking you H1 minus H9. What is the heat addition in the superheater, external superheater? What is the heat addition in the external superheater in kilowatt? Are you getting the idea, guys? In kilowatt means for getting this in kilo, because from this specific enthalpy you will get this in kilojoule per kg. But if you want this in kilowatt, तो आपको इसको mass of steam, how much is the mass of steam we are producing? H1 minus H9, then only you are going to get this in kilowatt. तभी आपके पास kilowatt में आएगा. Mass of steam you need to find out in kg per second. How much is the mass of steam is you are circulating in that plant in kg per second? If you will multiply by with H1 minus H9, you will get the heat added in the external superheater in kilowatt. But from where you will get mass of steam added? For that, you know, the total net work output of the plant is given to us 1 megawatt. And from that easily you will get. So first let me tell you how to write the energy balance for regeneration. How to write the energy balance? Guys, in GATE, you are going to get the question in which like one stage of regeneration will be there. Although there may be multiple stages. Okay, but I feel the chances are very less you will get those kind of questions. So at least these are kind of question you need to familiar. Earlier also some kind of energy balance question were asked, and easily you will be able to solve those questions if you will see here, if you will observe it here very carefully. So now how to write the energy balance, guys? What we are doing in open feed water heater, the superheated steam at this stage, this is the superheated steam, guys. We are taking the superheated steam from the turbine which is at a enthalpy H2. That superheated steam we are taking and directly we are mixing into what? The water, saturated subcooled water at this condition. So this is the water which is entering with enthalpy H5 in the open feed water heater. This is the enthalpy of the steam which is entering with enthalpy H2. They are mixing and finally they are settling at this particular enthalpy. Are you getting the idea, guys? So this is the steam. This is the steam entering with enthalpy H2. This is water entering with enthalpy H5. What is the increase in enthalpy of the water, guys? The increase in enthalpy of the water is H6 minus H5. H6 minus H5, this is the increase in enthalpy of the water. How much is the mass flow rate? कितना mass flow rate होगा? That will be what? क्या लिख सकता हूं मैं इसको? This is m fraction. This is m fraction. This is what? This is 1 minus m. So how much is the mass going out here? कितना mass जा रहा है? कितना? How much fraction of the mass of water is going? That is 1 minus m. So let me write it here, 1 minus m. Are you getting the idea, guys? So this is the energy. This is the energy enthalpy increase of the water. At 6 minus H5, how much is the fraction? The fraction is 1 minus m. 1 minus m, 1 minus m, 1 minus m, and here also you are having 1 minus m. Here you are having m. So this is equal to m into H2 minus H6. Are you getting the idea, guys? So this is the enthalpy balance for the regenerator, or what you can say for a open feed water heater. Energy balance for open feed water heater. M 1 minus m, because here m fraction you have taken, m fraction of steam you have taken from the turbine. 1 minus m is going where it is going to the condenser. Condenser load is going to decrease. Work output is going to decrease. In regeneration, work output is going to decrease. But why we carry out regeneration? For increasing the efficiency. The effect of the regeneration is to increase the efficiency. The work output is going to decrease. Okay, that's why I mentioned we use actually all these things in combination: reheating, superheating, and regeneration. At last, through simple 1 marks question, I will discuss some more about those superheating, effect of superheating, so that you will get a complete idea what kind of effect we are going to get with superheating, reheating, and regeneration. Chaliye. So this is energy balance. Let me further solve this. इसको मैं solve करता हूं. So this you can write it as H6 minus H5 minus m into H6 minus H5 equal to m into H2 minus H6. Okay, so if I will take this side, so H6 minus H5, this will be m into H2 minus H6, H2 minus H6 plus H6 minus H5. Yes or no? So I'm taking this term this side. I'm taking this term this side. Okay, so this will cancel out. So you will get this idea: H6 minus H5, this is equal to m into H2 minus H5. So how much is the fraction of steam you are taking? Many times it was asked in the earlier previous year question, how much fraction of the steam you are taking? How to calculate that? So simple formula is what? This is the simple formula: H6 minus H5 divided by H2 minus H5. This is the fraction of steam you are taking. What is H6? H6 is the final enthalpy of the mixture coming out from the open feed water heater, regenerator. So this is the final enthalpy. H5 is the enthalpy of the water, where before entering into the regenerator. H2 is the enthalpy of the steam before entering into the regenerator. H5 is what? Again, enthalpy of the water. Okay. So if you will put all these values here, what is H6, guys? What is H6? Now, can you tell me what is H6? Can you tell me what is H6, guys? H6 is nothing but this is Hg at 0.4 megapascal, because you are taking the steam at a pressure 0.4 megapascal. So not Hg, HF, sorry. This is HF. Okay. HF at 0.4 megapascal, because this is the saturated liquid line. This is saturated liquid line. So HF at 0.4 megapascal. So which table you will use, guys? This particular table. So at 0.4 megapascal, what is HF? It is 604.65. 604.65. Okay, so let me put this value here. 604.69. I think this is the answer, right? 604.65 है ना? 604.65. चलिए. So this is H6. What is H5, guys? What is H5? What is H5? H5 क्या है? This is the point H5. From where you will get H5? H5 कहां से आएगा आपका? The process is same. How to find out H5, guys? Try, apply your mind. H5 is nothing but H4 plus WP1. Guys, this 4 to 5 is the pumping process, WP1. This 6 to 7 is the pumping process 2, WP2. This is WP1, 4 to 5, 6 to 7 is WP2. Are you getting the idea? Let me zoom it for you again so that you will be able to observe it here. 1 to 2, expansion in the turbine with entire total mass. Now you have taken some steam out of the turbine. Now the expansion will be for remaining mass 1 minus m. Okay, this is the rejection, heat rejection in the condenser with the mass 1 minus m fraction. This is pumping process, WP1. This is the heat addition. Okay, Sunil, Sunil, different region students are there. Some of the South students are also watching this lecture. So I'm mixing Hindi, English both. Okay. So this is heat addition in the regenerator 5 to 6. Again, this is WP2. Let me mark it here. This is WP1, WP1. This is WP2, WP2, pumping process 2. So can I write it here? H5 equal to H4 plus WP1. Yes or no? Yes, I can write it something like this. So what is H4? H4 is nothing but HF at condenser pressure. What is condenser pressure? It is 7.5 kilopascal. So at 7.5 kilopascal, you can refer to the table and you can write it here HF. So HF at 7.5 kilopascal. So this is the 7.5 kilopascal, and here you are having HF 168.75. 168.75. So let me write it here. Okay, chaliye. So let me mark it here. Okay, H4. So H4 is what? 168.75. 168.75. What is WP1? It is nothing but V4 into 400, because 0.4 megapascal means, guys, 0.4 megapascal का मतलब क्या होगा? Because you are having 0.4 megapascal, so let me multiply by with the 1000. अगर मैं इसको 1000 से multiply करता हूं तो you will get 400. Okay, 400 kilopascal. 400 multiplied by what is the condenser pressure, guys? The condenser pressure is 7.5. So what is V4? V4 is this. At condenser pressure, what is VF? At condenser pressure, what is VF? It is this 0.00100,800. So this is V4. So if you solve this all, you will get H5. So let me mark it here, H5. H5. Narendra, I think if you want all those recorded lecture, then you need to join us. Okay. If you want to watch these lecture on YouTube, you will find daily basis, but those are going to remain for some particular amount of time only. During the class only, you need to watch the live session. But if you want these sessions like some kind of recorded lecture, if you want, then you need to join us. You need to talk to the representative. You can go to our YourPedia website. You will find some information there. Okay. Chaliye. Not only this assignment, guys, other than this also you will get test series, lots of things you are going to get. Practice question, Fundu series. On YouTube we discussed only Fodu series. We discussed only 4 to 5 question on YouTube. But Fundu 5 series exclusively we covered for our all students, okay, which are actually directly connected with us. So you will get Fundu 15 series also on the YourPedia panel. You will get all those recorded lecture also. So 400 minus 7.5 multiply by 0.00100,800 plus 168.75, you will get H5 169.14564 kilojoule per kg. Okay, so this is H4, H5 we are going to get. Okay, this is H5 we are going to get 169.14564. So now let me check. We are having the H5 value. We are having the H5 value. What is H2 guys? H2 क्या होगा? What is H2? From where you will get H2? H2 directly you will get from the property table. H2 directly you will get the property table. This property table guys. 0.4 megapascal for the superheated steam. 0.4 megapascal at this particular temperature. You can check it here. Their entropies are almost same. So 1 to 2 is isentropic expansion. 1 to 2 is isentropic expansion. So this entropy is almost same. So at 0.4 megapascal, because this point is going to lie in the superheated region, because here if you will check 0.4 megapascal pe, if you will check the VSG, so this is 6.89, which is very less as compared to 7.26. This process is isentropic expansion. So you cannot say, ki, sir, this H2 will be Hg. You cannot say why? Because here if you check the entropy, this is 6.89, and here in this superheated table if you check the entropy, this is 7.26. This is very close to this 7.2586. So from this you can say, okay sir, this is our H2, this is H2 2902.6. Okay, so let me mark it here. 02.6 minus what is H5? H5 we calculated 169.145. 169.145. So 169.145. If you solve, you will get the fraction of the stream which is bleeded out from the turbine. Okay, steam turbine. So let me write it here. 604.65 minus 169.145 divided by 2902.6 minus 169.145. If you will solve, you will get 0.1593. So 0.1593. This is the fraction of stream. This is fraction of the steam we are taking from the steam turbine. 0.1593. Okay. Now guys, what is given to us? What is given to us? The net work output of the plant is given to us. What is W net? The W net of the plant is given to us, which is 1 megawatt. The W net of the plant is given to us 1 megawatt. 1 megawatt. Okay. And how you can write this 1 megawatt, guys? This 1 megawatt, you can write it here. This is equal to the turbine work. The turbine work, which is nothing but H1 minus H2. Let me write it here, because with H1 minus H2 you will have total friction. So let me write it here something like this. This is mass of the steam, total mass of the steam, guys. Because this is in megawatt. 1 megawatt is a power which you are producing, net work output. So mass of the steam into how much is the expansion with the total steam, that is H1 minus H2. This is the expansion with the total friction. So you can write it here 1 into, if you want to write it here 1, because this is the total friction with the total steam, 1 into H1 minus H2. Okay, plus how much is the expansion with the remaining steam? 1 minus m, because m you have taken out, m amount of the fraction of the steam you have taken out. So the remaining expansion will be 1 minus m into H2 minus H3. H2 minus H3. Okay. Are you getting the idea, guys? So H1 we know already. H2 also I told you how to get. M also we calculated. H2, H3 also easily you will get from the table. So from solving this, you will get the mass of the steam circulated. You will get the mass of steam circulated. So let me put it here, all the values. So what is H1? H1 is this superheated table, 600 degrees Celsius, 5 megapascal. 600 degrees Celsius, 5 megapascal. So this is H1, 3666.8. From the superheated property table, you will get this data. superheated property table, you will get this data. So let me write it here. 3666.8. What is H2? H2 is a point here. Again in the superheated region. 0.4 superheated region. 2902.6. 2906.2. 2902.6. 02.6. So this is H2. 1 into this is mass of the steam, total mass of the steam, plus 1 minus m, and m we calculated. Let me mark the value of m also here. 0.15932. This is m into H2 minus H3. What is H2? What is H2, guys? H2 is 2902.6 minus H3. H3 you need to calculate, guys. H3 आपको निकालना पड़ेगा. Let me check. So show it here. How to get the H3? Can I get some answer from you guys? How many of you will be able to find out this H3? How to find out this H3? कैसे निकालोगे इस H3 को, guys? So this 0.223 is what? Isentropic expansion. 223 is isentropic expansion, means S2 equal to S3. What is S2? What is S2? S2 equal to, at this pressure, what is S2? S2 is 7.2586. This is S2. Okay. This is S2. What is S3? S3 is equal to this only. S2 equal to S3. S2 equal to S3. Both are same. S2 equal to S3. Yes or no? This expansion, guys, this expansion. What is S2? S2 is the superheated, for the superheated steam at a pressure 0.4 megapascal. So at 0.4 megapascal, what is the entropy? 7.2586. This is S2, and S2 equal to S3. And how we can write S3? S3 is in the wet region. This you can write it as SF. Okay. And what is SF here? At condenser pressure, if you will check, this is nothing but 7.2586. This is equal to this 0.57627 plus x into SFG. What is SFG? 7.6738. So you will get a dryness fraction at the exit of the turbine. You will get a dryness fraction at the exit of the turbine, means you will get X3. So how many of you are getting X3, guys? Please confirm. How many of you are getting X3? Okay. So let me write it here for you. 7.2586 minus 0.57627 divided by 7.6738. You will get x equal to 0.87. X equal to 0.8707. This is the dryness fraction at the exit of the turbine, guys. Dryness fraction at the exit of the turbine. Okay. Dryness fraction at the exit of the turbine. Now, how to find out H3? How to find out H3, guys? Let me zoom out and let me write it here. H3. So H3 is nothing but HF at condenser pressure पे HF. So at condenser pressure, what is HF? HF is given to us 168.75 plus X, and we got the value of X, which is equal to this 0.8707 into HFG. What is HFG at condenser pressure? HFG at condenser pressure is equal to 2405.3. 2405.3. So guys, all these data I'm putting from this property table. So at the condenser pressure, this is HF 168.75. This is HG 2405.3. Okay. So if you'll put these data here, you will get H3. Enthalpy at the exit of the turbine. So 2405.3 minus 0.8707 plus 168.75, you will get H3 2573.1793 kilojoule per kg. So now this is 1 megawatt, means 1 into 10 की power 3 kilowatt. Yes or no? So this 1 megawatt you can write it as 1000 kilowatt. Okay, so 1000 kilowatt equal to mass of steam is equal to this. We calculated H3 also. So now if you will put all this data, you will get a mass of the steam circulated. You will get the mass of steam circulated. Okay, so let me put this data here. So 2902.6 minus 2573.1793 multiply by 1 minus 0.15932 plus 3666.666.8 minus 2902.6. Okay, so this you will get mass of steam, you will get 1000 divided by this, you will get 0.9604 0.9604 kg per second. This is the mass of the steam you are going to get. 0.9604 mass of the steam you are going to get with this. Mass of the steam will be 0.9604. Okay, guys. So now if you will put this data here, because we want how much is the heat we are adding into the superheater, H1 minus H9. So how much heat added in the superheater, that is equal to mass of steam into H1 minus H9. H1 minus H9. Okay, so this is equal to 0.9604. What is H1? H1 is the enthalpy of the superheated steam at the entry of the turbine, and that is nothing but, for the superheated steam table, if you will check it here, 5 megapascal, that is 3666.8. So 3666.8. 3666.8. What is H9? H9 is nothing but Hg at boiler pressure. Hg at boiler pressure. So here if you will check this property table, Hg at boiler pressure. Hg at boiler pressure. This is nothing but 2794.2. 2794.2. So guys, if you will put this, you will get the heat supplied. Let me check all the calculations. So 3666.8 minus 2794.2 multiply by 0.9696. Okay, so please check. So that is, let me check my answer also. So H1 minus H9, that is 872.2794. Mass of the steam, guys, we are going to get 0.7682. So I think there is some calculation mistake. Let me check it here again. The mass of the steam which we calculated, let me again check it here. So that is 1 into 1 minus m we are getting right, exactly right. Let me check here again the calculation for the mass of the steam. So that is 1 megawatt. So let me put it here, 2902.6 minus H3 we got close to 2573.1793 multiply by 1 minus m, so that is 1 minus 0.15932 plus 3666.8 minus 2902. So 3, this is H1, H2. H2 is this only. Let me check it here. This is H1, this is H2, this is M. Okay, H2 is also this. Let me check again for H3. H3 के लिए मैं दोबारा check करता हूँ बच्चों. Dryness fraction we got close to 0.87. 0.87. Yes, that is close to 0.87 only. So H3 is going to H3 will come out close to 2263. ये 2263 आना चाहिए बच्चों. Let me check it again. This will come out 2263 because when I earlier calculated, that will come out 2805. So 2263.2805. So let me check it again. HFG, so that is 2505. Yes. Yes, actually there is some calculation mistake. Exactly, you will get this only. Everything is right. Only actually we did some mistake in just adding these two quantities. So if you will add it here, guys, you can check it here. This is 2405.3 multiply by 0.8707. You will get 2094 plus 168.75. If you will carry out this exercise, you will get this value H3 you will get 2263.04. This is H3 you are going to get, guys. This is H3 you are going to get. Okay, and if you will put this value of H3 here, you will get mass of steam 2902.6 minus 2263.04 multiply by 1 minus 0.15932 plus 3666.8 minus 2902.6. 1000 divided by this, you will get this 0.7681. This is the mass of the steam, guys. You are going to get 0.7681. Yes, you are going to get the mass of the steam 0.7681. Please check. And if you will put this value here, mass of the steam 0.7681 into this, you will get the answer in the range, I think 366.8 minus 2794.2. So exactly answer you will get 670.269 kilowatt. This is the heat addition in the external superheater. This is the heat addition in the external superheater, guys. So please check your answer. Let me show you the range also. The range which is exactly given for this question is this: 660 to 685. 660 to 685. This is the range given. Very lengthy, but if you follow the process, you will get the answer. Vijay Raju, your answer is right. Very good. Very good, Vijay. Chaliye. So, like lengthy question, but I hope you all are following me. Okay, chaliye, good. So I hope you all are getting this answer, 660 to 665, and we got exactly mid of this, close to that, 670. We got the answer, and yes, that is in this range, so our answer is right. Chaliye, let us now move to next question, guys. Question number 12. Now I think the question are slightly, comparatively they are not that much lengthy. Next three questions. So 12 to 14 we are having common data question. So now you can slightly relax. Okay, and last 10 questions I am going to complete in 10 minutes only. Don't worry about that. So first 10 questions, those are comparatively lengthy because through these we discussed every single concept related to those Rankine cycle. I'm focusing. I'm not saying the power plant in GATE question, guys. If you analyze the previous year question, most of the question you will find from Rankine cycle only. But other than those, there are some questions, objective questions you are going to find related to combined cycle, Bottman cycle, okay, topping cycle. Those things I'm not discussing here. How to solve the problems related to Rankine cycle, that is our target. Why to subtract pump work? Where pump work kahan subtract kiya maine? Let me check where I subtracted the pump work. Actually, I did here H5 equal to H4 plus WP. Where you are saying ki I subtracted the pump work? Let me check. I'm not getting any point where actually I subtracted the pump work. Okay, so please message me again. Chaliye, next question, guys. Let me zoom it for you. So 12 to 14 we are having common data question. 12 से 14 जो question है वो है common data. So one time you need to apply your mind and you will get the question one to one. Assignment, Vinod, you will get on the your email. Like if you just, in the description of this video, you will find some Google form. If you fill that Google form, you will get the this assignment you will get. Okay. Chaliye. So a steam power plant in a region operates on a real Rankine cycle, has a net power output of 60 megawatt. 60 megawatt. Steam enters the turbine at 7 megapascal, this temperature. So at 7 megapascal, if you check the saturation temperature, this means you are having the superheated steam. हमारे पास क्या है बच्चों? We are having the superheated steam, and it is cooled in the condenser at a pressure 10 kilopascal, means the condenser pressure is 10 kilopascal. So at 7 megapascal, we are having all properties. At 10 kilopascal, we are having all properties. The mass of the steam circulated is 4,000. Acha, 4,000 is the mass of the water circulated in the condenser. If the isentropic efficiency of the pump and turbine are these are the isentropic efficiencies of pump and turbine, then estimate the thermal efficiency. Very good question. Now he has given you the isentropic efficiency of the turbine and pump. He's asking you what is the cycle efficiency. So the question is almost same, but the cycle is not ideal. The cycle is not ideal. So now let me write it here, something like this. Guys, using this cycle, if I will ask you, can you find out the isentropic work of the turbine? Isentropic work निकाल सकते हो? Isentropic work निकाल सकते हो turbine का? Yes, sir. We can easily find out using the property table. Okay. So what is isentropic efficiency? Isentropic efficiency of the turbine is given to us, and this is nothing but 75%. Okay. Pump and turbine. So for pump it is 80. For turbine it is 80%. So the isentropic efficiency of the turbine is 80%. So this is nothing but W actual divided by W isentropic. So isentropic work you will get from the basic formulation, and if you will use this relationship, you will get the actual work of the turbine. आपके पास क्या आ जाएगा? Actual work आ जाएगा बच्चों. You will get the actual work. Please try to solve. Similarly, if you will solve it for the actual, pump work, isentropic pump work, that is nothing but again V1, because this point is mentioned as here V1. So V1 into the boiler pressure minus condenser pressure. Boiler pressure minus condenser pressure, because here this cycle diagram is given to us, and in this cycle he mentioned this point as 3, this point as 4, this is 1, this is 2, something like this. So you will be easily able to get the pump work also. This pump work is nothing but H2 minus H1. H2 minus H1, isentropic work. And W actual will be what, guys? This will be WP isentropic divided by the isentropic efficiency of the pump. Okay, why? Because for pump, the isentropic efficiency is the W pump isentropic divided by W pump actual, because pump is a work absorbing device. So for any work absorbing device, the isentropic efficiency will be work actually isentropically given, because that will be less. Work isentropically given divided by the work which is actually given to that device. We know I cannot say. You can call. Okay, you can call. Some number you will find on the YourPedia website. You can call on those number. Okay, then only you will get the information. Or you can just give me some time. I need to confirm. Okay, this time I cannot say you will get it for mining, but for all other branches like CSC, electronics, you are going to get all different type of assignments for each and every subject. Just you need to register on the Google form. If you will fill that Google form, if you will put all those information, you will get. Okay, for all branches you will get, but for mining I cannot confirm. Just give me some time. Okay, so chaliye. So W pump isentropic, this is nothing but this H2 minus H1, and this if you will divide by isentropic efficiency of the pump, which is given to us 0.75, you will get the actual pump also, actual pump work. You will get the actual pump work. Okay, and now if you will find out all those things, the process is going to remain same. So what is cycle efficiency, guys? The cycle thermal efficiency is nothing but W turbine actual minus W pump actual divided by heat supplied. ओके, सो क्वेश्चन बन जाता है थोड़ा सा अच्छा. हाउ? Because isentropic efficiency of the turbine, this is isentropic efficiency of the turbine is nothing but the actual work you are going to get, means H1 minus H2 dash divided by H1 minus H2. This is isentropic work, this is non-isentropic work. Isentropic work, non-isentropic work. So from this you will get H2 dash. यहां से solve करोगे तो आपके पास H2 dash आ जाएगा. You will get the H2 dash. Similarly, for pump, the isentropic efficiency is 0.75. So this is isentropic efficiency of the pump. So this is nothing but, okay, note H1. यहाँ मैं H1 नहीं लिखता. Let me note right here H1 because in this question he has given you the points something like this. Let me use those points only 3 to 4. Okay, 3 to 4. So let me write it here. H3 minus H4 dash by H3 minus H4. This is isentropic expansion. This is non-isentropic expansion. So from this you will get H4 dash. Similarly, for the pumping processes 1 to 2, actual work given will be more. So this is H1 minus H2 minus H1, because I think 2 to 1 is a pumping process, and here you will get H2 dash minus H1. So solving this you will get H2 dash. इसको solve करोगे तो क्या मिलेगा आपको? H2 dash. Are you getting the idea, guys? You will get H2 dash. Now in this question he is asking you the thermal efficiency. Why actually I calculated all those things? Because turbine actual work easily you will be able to calculate. Pump actual work you will be easily able to calculate. What is heat supplied? So the actual heat supplied will be W turbine actual, W pump actual divided by heat supplied will be this H3 minus H2 dash. This will be H3 minus H2 dash. Are you getting the idea, guys? This H2 dash is required because then only you will be get the actual heat addition. H3, this particular point, guys, this particular point, this is H3, but heat addition will be what? Because here you are not having isentropic compression, you are having irreversible adiabatic expansion. So the heat addition, suppose this point is 2 dash, so the heat addition will be H3 minus H2 dash. Are you getting the idea, guys? This is the heat addition, H3 minus H2 dash. That's why here I have written here, this formula. From this you need to calculate H2 dash so that you will be get the actual heat addition, and then if you will take their ratio you will get the cycle efficiency. Guys. So please check and confirm. Are you getting any answer, guys? Okay. So the W turbine isentropic, this will be W turbine isentropic will be H3 minus H4. So H3 will be what? From where you will get H3, guys? From the superheated steam table. From the superheated steam table you will get H3. So that if you will check you will get 3411.4. So I'm writing this from this here. You can check from the superheated steam table at 7 megapascal. This is the enthalpy 34114. Okay, this is H3. This is H3, guys. Okay. Similarly, what is H4? H4 कहां से आएगा? From where you will get H4? For H4 you need to equate S3 equal to S4. Okay, so what is S3? S3 is SG here. This is S3 6.8 This is equal to S4. This is nothing but SF. At condenser pressure, we are having SF 0.64920 plus X into SFG, which is 7.4996. So you will get the dryness fraction at the turbine exit. You will get the dryness fraction at the turbine exit. So 6.8 minus 0.64920 divided by 7.4996. You will get dryness fraction X equal to 0.82015. So what is H4? H4 will be again HF. What is HF? At condenser pressure, HF is 191.8 plus X, which is 0.82015 into HFG, and HFG at condenser pressure is this 2392.1. 2392.1 plus 191.8. So you will get this H4 equal to 2153.68. This is H4. And if you'll put this data here, 2153.68, you will get W turbine isentropic. W turbine isentropic. एक ही बार करना पड़ेगा बच्चों. For question number 13, 14, you need to solve all these things again because those are common data question. Okay, easily you will be able to utilize this data in that question. So 3411.4 minus answer. So the W isentropic is 1257.71 kilojoule per kg. This is the turbine work isentropic. What is turbine work actual, guys? Actual कितना होगा? Actual will be 80% of this. Why? Because the isentropic efficiency of the turbine is 80%. So just you need to multiply this quantity with 0.8. You will get this isentropic turbine work equal to 1006.174 kilojoule per kg. So this actually we are getting from 0.8 into 1257.71. From this you will get W turbine isentropic actual. W turbine actual you will get. Let me also check my answer. W turbine actual we will get in this range. Yes, 1006.168. Very good. Actual work you will get in this range. Now if you will compare this, okay, let me solve this also. Okay, let us find out for pump also. Pump के लिए भी निकालते हैं बच्चों. Let us find out the pump work also. So WP isentropic is nothing but V3. What is V3? How much volume? The condenser at condenser end you are handling, that is this 0.00101027 into the boiler pressure, which is 7000 kilopascal, minus the condenser pressure, which is 10 kilopascal. So if you will solve this, you will get isentropic pump work. You will get isentropic pump work. So 7000 minus 10 multiply by 0.00101027. You will get 7.06178 kilojoule per kg. So this is pump work isentropic. But what is pump work actual? For this, you need to divide this by 0.75. 7.06178. If you will divide it by 0.75, why? Because the isentropic efficiency of the pump is given to us, which is 75%. So if you will divide it by 0.7, you will get this 9.4157 kilojoule per kg. So this is actual work given to the pump. This is actual work given to the pump. Okay. So we calculated the actual work given to the pump also, actual work divided by the turbine also. Okay. Now let us find out the enthalpy at the exit of the pump. H2 dash. enthalpy at the exit of the pump. So that is nothing but H3, this particular enthalpy, guys. Because if you want to find out the heat addition, so this point is 1 to 2, 1 to 2 dash. So if you want to write here the 2 dash, so what is 2 dash, guys? What is 2 dash? Can I write this H2 dash equal to H2 because this point, let me write it here. This enthalpy, this is 3 to 4, this is 1 to 2. Okay, 1 to 2. So if you want to write it here, H2 dash, so that is nothing but H1 plus WP actual. Are you getting the idea, guys? WP actual. Okay, because WP actual is nothing but H2 dash minus H1. Enthalpy at the exit of the pump in case of non-isentropic irreversible adiabatic expansion compression, sorry, and this is the entry to the pump. Why actually I'm using 2 and 1? Because those points are given to us. Okay, he used that kind of numbering, so I'm using those only. So from this you will get H2 dash. So H1 is what? H1 is nothing but, what is H1? H1 is nothing but HF. This particular point, guys, this particular point is H1 because these points are given to us. Let me again show here. This point is 1, this point is 1, this is 1, this is 2, this is 3, this is 4. Okay, so H1 is nothing but HF at T condenser. So this H1 is nothing but at T condenser. What is HF? Is 191.8 kilojoule per kg. So if I will use it here, 191.8 plus WP actual is 9.4157. So you will get H2 dash. So H2 dash is equal to 191.8 plus 9.4157. You will get 201.2157 kilojoule per kg. This is H2 dash. This is H2 dash. Okay. Now what is heat supplied, guys? Heat supplied in the boiler is nothing but this is 1 to 2, 2 to 3. So this is H3 minus H2 dash. H3 minus H2 dash. What is H3? H3 from the superheated table we already calculated. We already mentioned this H3, guys. Yes or no? From the superheated property table, let me again show you here. For the steam turbine exit from the boiler or entry to the turbine, this is 0.3. So H3 is nothing but 3411. Enthalpy for the superheated steam at the entry to the turbine, 3411. Okay, so 3411.4. So 3411.4 minus H2 dash is 201.2157. So heat supplied you will get 3411.4 minus answer, you will get 3210.1843 kilojoule per kg. This is the heat supplied in the boiler. This is heat supplied in the boiler. Okay, guys. Now, if you want to find out the actual thermal efficiency क्या होगा बच्चों? Let me write it here. The actual thermal efficiency for this question, the thermal efficiency for this question will be W net divided by heat supplied. So this is W turbine actual minus W pump actual divided by heat supplied. So what is W turbine actual, guys? W turbine actual, how much turbine work actually we calculated? It is 1006.174. How much is that pump work actually we calculated, guys? This is nothing but 9.4157. 9.4157 divided by heat supplied. How much is the heat supplied? 3210. 3210.1843. So if you solve this, you will get the efficiency, the actual thermal efficiency, the thermal efficiency for this cycle. The thermal efficiency for this cycle. So let me solve it for you guys. 1006.174 minus 9.41 57 divided by answer, you will get 31.04. 31.04. Yes, 31. 31, if you are getting the answer 31, your answer is very right. If you're getting the answer 31, your answer is right. So the thermal efficiency for this question, you will get in the range of 31.04%, and option A is the correct answer for this question. Option A is correct. I hope you all are getting this answer. Yes, Chaitanya Vijayaraju, your answer is right. 31%. Very good. Okay, let us now quickly end those questions with reference to question number 9. What is the mass flow rate of the steam? He is asking you what is the mass flow rate of the steam. With reference to the same question, if you will refer, what is the mass flow rate of the steam? कैसे निकालोगे mass flow rate of the steam? Okay, net work we calculated, guys. Let us see. Net work is given to us. Net work for this particular question is given to us. Let me zoom it for you here. Net work is given to us, which is nothing but 60 megawatt. This plant is of 60 megawatt. 60 megawatt ka plant hai bachon. 60 megawatt. And how much net work we calculated, guys? Actually, net work we calculated something like this. The difference of this turbine and this. Okay, this is actual network. This is the actual network. So let me solve it here only, that particular question. So the 60 megawatt means 16 to 10 ki power 3. That is nothing but mass of steam into W net in kg, kilojoule per kg. So mass of steam is equal to W net. How much is W net, guys? This is W net. 1006.174 minus 9.4157. If you will write it here, you will get this 996.75. 996.75. So the mass of steam circulated in kg per second. So 60, if you will divide by this, you will get this answer in the range of 60.195 kg per second. Mass of the steam 60.195 kg per second. Are you getting the idea, guys? This is the actual turbine work. This is the actual pump work. Actual turbine work minus actual pump work, you will get W net. W turbine actual minus W pump actual, you will get net work. Net work in kilojoule per kg, multiply by the mass of steam in kg per second, you will get the net power in megawatt, kilowatt, because unit we need to balance. So this also I am taking in kilowatt, and this also product is in kilowatt. You will get mass of the steam 60.195. Let us see. Yes, exactly answer. Like we are getting the answer 60 kg per second. 60 kg per second. Are you getting the idea? So option D is the right answer for this question. 60 kg per second. Very good. Let us quickly move to next question. Question number 14. Question number 14. With reference to question number 9, determine the temperature of the cooling water rise. Take specific heat of the water. How much is the rise in the temperature of the cooling water? How much is the rise in temperature of the cooling water? You know, guys, heat rejection in the condenser, that is nothing but H3, H4. Okay, that is 1 to 2, 2 to 3, 3 to 4. Yes, so that is because here the cycle which we have, which is given to us, the cycle which is given to us, let me again check this cycle. So this is 3 to 4. Yes, 3 to 4. Okay, 3 to 4. So rejection in the condenser is nothing but H4 dash minus H1. H4 dash minus H1. This is rejection into the condenser. This is rejection into the condenser. Multiply by mass of the steam. Mass of the steam. Yes or no? How much mass of the steam you are circulating? 60 kg per second. So H4 dash minus H1. This is the enthalpy at the inlet of the condenser. Okay, why actually I'm not writing H4? Because that will be different. You may get answer close to that. Okay, even if you will take H4, because the turbine isentropic efficiency is 80%, but in right direction, right case, you need to take it here H4 dash. Why? Guys, this expansion, let me draw here that cycle. This is the cycle given to us. This is a cycle which is given to us. So here he mentioned 0.1. Okay, something like this. So this is 0.1, this is 0.2, this is 0.3, and this is 0.4. Something like this. Something like this. Okay. But what I assume, guys, let me take it here more clearly, so that something like this. So this is 3, this is 4. But if you will go with non-isentropic expansion, so this is the point. This is the point which is 4 dash. This point is 4 dash. This point is 4 dash, guys. This point is 4 dash. So the heat rejection in the condenser, is nothing but H4 dash minus H1. Are you getting the idea? Okay. And similarly here, because here we have taken point 2 dash. We have taken this point 2 dash for the heat addition. Heat addition is nothing but H3 minus H2 dash. You know the idea, guys? Because this is the point, because condensation, this compression and expansion are non-isentropic. They are not reversible adiabatic. They are irreversible adiabatic. And in case of irreversible adiabatic, this will be the point. This will be the point at the exit of the pump 2 dash, and this will be the point at the exit of the turbine. So the heat addition will be H3 minus H2 dash, and heat rejection will be H4 dash minus H1. So H1 we know directly from this, you will get the H1, because from the condenser at condenser pressure, what is HF? This is this. So H1 is nothing but 191.8. This also we calculated mass of the steam. Mass of the steam, this is 60. This is 60. Okay. But from where you will get heat H4 dash? H4 dash kahan se aayega bachcho? From where you will get H4 dash? So H4 dash, you know, this W turbine actual is nothing but H3 minus H4 dash. H3 minus H4 dash is your W turbine actual. So H4 dash is nothing but H3 minus W turbine actual. So what is H3? H3 is the enthalpy of the superheated steam at the entry of the turbine, which is 3411.4. 3411.4. And what is turbine work actual, guys? What is the turbine work actual? What is turbine work actual? For that, you need to refer to this initial information, because here we calculated the actual turbine work. Somewhere here, let me write it here. The actual turbine work. The actual turbine work. I think we are having somewhere here. Yes, 106.174. 1006.174. Okay. So this is 1006.174. So you will get H4 dash. Okay, guys. So 3411.4 minus 1006.174. You will get this H4 dash. H4 dash equal to 2405.226 kilojoule per kg. Kilojoule per kg. Okay. And this, if you will put it here, 2405.226 minus 191.8 into 60, you will get the heat rejection in the condenser. So let me solve it for you. So minus 191.8 multiplied by 60. So this quantity will come out equal to 132,805.56 kilojoule per kg. This is the heat we are rejecting into the condenser. This is the heat we are rejecting into the condenser. He's not asking you heat rejected into the condenser. He's asking you the rate of increase of the temperature of the cooling water. What is the rate of the increase of the temperature of the cooling water? Guys, if you refer to the data which is given to us earlier, mass of the cooling water circulated is given, which is 4000 kg per second. Mass of the cooling water circulated given to us is 4000 kg per second. So if you put this data here, because this is heat rejected, this heat we are rejecting to what? We are rejecting heat to the cooling water. So this we can equate it with 4000 mass of the cooling water into Cp of the cooling water, okay, into change in temperature of the cooling water. This is nothing but heat rejection in the condenser. Yes or no? How much heat you are rejecting into the condenser? That is equal to the mass flow rate of the cooling water, specific heat of the cooling water, change in temperature of the cooling water. So mass flow rate is given to us 4000. Specific heat is also, he mentioned, take it as 4.18. So 4.18 delta T we want to find out. So solving this, you will get the change in temperature of the cooling water. Very simple question. Change in temperature of the cooling water also you will get. So let me solve it for you guys. So 132,805.56 divided by 4000 divided by 4.18, you will get this close to 7.94 degrees Celsius. This is the change in temperature of the cooling water. Change in temperature of the cooling water. So guys, for this question, the right answer is what? Option A itself. Option A, 8 degrees Celsius is the change in temperature of the cooling water, is the right answer for this question. Very good. 7.9429, this is the change in temperature of the cooling water we got. I hope you got the idea, guys. He asked you about the how much is the change in temperature of the cooling water. So first we calculated how much is the heat rejection. For that, first we calculated the H4 dash. Okay, because the heat rejection will be H4 dash minus H1. H4 dash we calculated using the isentropic efficiency relationship, and then we, this is nothing but HF at the condenser pressure. We calculated the heat rejection, and that heat rejection remaining we equated with this. So calculation is there, but concept wise it is very easy. Calculation is there on all those, these type of question, they are comparatively lengthy. Calculation you will find. Chaliye. So question number 15, guys. 15वां question है. 15th question. Last numerical question, guys. Then we will move to simple direct question only. Last numerical question. A steam power plant operates on an ideal Rankine cycle with one open feed water heater. So this is open feed water heater, guys. This is open feed water heater. You are taking the M fraction of the mass you are taking. Determine the fraction of the steam extracted from the turbine. How much fraction of mass you are extracting? How much fraction of mass you are taking? So enthalpy is given to you, H2 is given to you, H4 is given to you, H6 is given to you. Let me zoom it for you guys so that you will be able to observe this. So he is asking you, in this question, he is asking you, how much is the fraction of mass of the steam you are taking? How much fraction of the mass of the steam you are taking from the turbine? So let me write it here, the energy balance. Energy balance likhte hain. What is the energy balance, guys? The energy balance is here. You can write it here. What is the mass here? Kitna mass hai? M. So M into H2 minus H6. M H2 minus H6. That is equal to 1 minus M, because here how much is the mass? 1 minus M. M fraction is here and the remaining mass is going 1 minus M fraction. So M into H2 minus H6 into equal to 1 minus M into H6 minus H5. This is H6. This is H5. This is the change in enthalpy of the water. This is change in enthalpy of the steam which you are taking from the turbine. This is change in enthalpy of the steam. H2 minus H6. This is change in enthalpy of the water. So this is the energy balance for the open feed water heater, something like this. So if you will solve this, अगर इसको मैं solve करता हूँ, so m H2 minus H6, okay, plus m into H6 minus H5, that is equal to H6 minus H5. So m I can take common, this is H2 minus H6 plus H6 minus H5, that is equal to H6 minus H5. So m equal to H6 minus H5 divided by, this is H2 minus H6 tha na? This is H6 guys, this is H6. So this will cancel out because this is H2 minus H6. So this will cancel out. You will get H2 minus H5. So now you can refer to this diagram. The information, all informations are given to us, guys. All information are given to us. What is H6? H6 is 750. So you can write it here 750. What is H5? H5, this H5. So let us see what he mentioned about the pump work. Pump work के लिए उसने क्या mention किया है? A power plant with one open feeder determine the fraction of the steam extracted from the turbine. The enthalpy is at various states. Neglect pump work. Neglect the pump work. So if you are neglecting the pump work, you can say H4 5 is almost equal to H4. Yes or no? If you are neglecting the pump work, by neglecting the pump work, you can say this enthalpy at the exit of the pump, because this is WP1 and WP is 0. Suppose if this is 0 neglected, if you neglected this pump work, so this enthalpy, exit enthalpy will be almost equal to the inlet enthalpy. Yes or no? So H5 is almost equal to H4 and H4 is given to us 190. So in place of H5, you can write it as H4, which is given to us 190, divided by H2 minus H5. H2 is 2560 minus 190. So if you will solve this, you will get the fraction of mass you are taking from the steam turbine. Fraction of the mass of the steam you are taking from the steam turbine for the regeneration purpose. So let me solve 2560 minus 190. So you will get this mass equal to 0.2362. So 23% of the steam, 23% of the steam we are taking from the steam turbine, means option B is the right answer, guys. 23.6, option B is the right answer. Accepted answer, option B. Very good. I hope this question is clear to all, guys. Yes, fine. Okay, now we are going to move towards 1 marks question. Chaliye. So let me quickly cover all these 1 marks question also. Question number 16. Question number 16. In a reheat Rankine cycle. Reheat Rankine cycle. Why we carry out reheating, guys? Reheating we carry out for increasing the quality of steam at the exit of the turbine, for increasing the net work output of the cycle. So if you want to improve the net work output, if you want to improve the quality of steam at the turbine exit, then we go with the reheating. Reheating is not going to result in the increase in efficiency. It can result if the reheat pressure, like the ratio of the reheat pressure reheat pressure divided by the pressure of the boiler, if they are in the range of 0.2 to 0.25, means if the reheat pressure, simply what you can say, if the reheat pressure is 20 to 25%, 20 to 25% of boiler pressure, then you will get the maximum efficiency. Reheat pressure 20 to 25% of the boiler pressure, you will get maximum efficiency. But if the reheat pressure is very close to the boiler pressure, then efficiency change will be 0. Why? Because you are not using reheating. If you are decreasing the reheating pressure, guys, decreasing reheating pressure, why actually we are decreasing reheating pressure? The decrease in reheating pressure will result in the more quality of the steam at the turbine exit. Something like this. So something like this. So this is the superheating, and suppose you are using very low reheating, both low reheating use kare. For example, you are using very low reheating, so this quality of the steam is going to increase, X will increase. Are you getting the idea, guys? By decrease in reheat pressure, the quality of the steam will increase. वर्क आउटपुट इज ऑल्सो इंक्रीजिंग, बट द एफिशिएंसी विल डिक्रीज. एफिशिएंसी क्या हो जाएगी? डिक्रीज करेगी. सो दिस इज अवर रीहीट प्रेशर. इसे मैं क्या बोल रहा हूं? व्हाट इज दिस? दिस इज प्रेशर रीहीट, रीहीट प्रेशर. So this is our boiler pressure. This is PV, boiler pressure. So if both are very close, then efficiency change will be less, negligible. Why? Because if at very high pressure you are carrying out the reheating, it means heat addition will be less. Suppose at here you are carrying out the reheating, then what will be the reheating heat addition? That will be negligible. It means the effect of the reheating will be negligible. So efficiency change will be negligible with very high reheat pressure. Okay, and this dryness fraction will also be less. At the exit of the turbine, the dryness fraction will also be less. Are you getting the idea? So we are interested in low reheat pressure, so that dryness fraction will improve. But with low reheat pressure, the efficiency will start decreasing. So maximum efficiency you will get when the reheat pressure, this pressure reheat, and the boiler pressure, this ratio is close to 20.2 to 0.25. Means the reheat pressure is 20 to 25% of the boiler pressure, then you will get the maximum efficiency. So reheating results in increasing the quality of the steam at the turbine exit, more W work, turbine work, net work will also increase. Efficiency can increase or decrease, it depends on the reheat pressure. So let us see what are the options given to us. Pump work input increases, reheat cycle say the pump work will increase, and moisture content at the turbine exit will remain same. No, this is not right. The pump work input remains the same, moisture content of the turbine exit decreases. This is also not same. Pump work will decrease and the moisture content at the turbine exit will decrease. So what will be the right answer, guys? The pump most okay, turbine exit decreases. The reheat Rankine cycle. With the reheat Rankine cycle, guys, we are carrying out the reheating. With the reheating Rankine cycle, so the quality is going to increase. तो यहाँ पे आना चाहिए क्या बोल रहे हैं? The same, the moisture content at the turbine exit. He is asking you the moisture content. यहाँ पे देखो थोड़ा सा ये point is slightly difficult. Moisture content, quality of the steam is increasing, means moisture content is decreasing. Are you getting the idea? So what I told you, if X is increasing, quality of steam is going to increase. So the moisture content will decrease. Are you getting the idea? So initially I just only refer to that what is the moisture content, but if the quality of the steam is increasing, moisture content is going to decrease. So this point is right, guys. This point is right. There will be no effect on the pump work and the moisture content is going to decrease. Why? Because X is increasing. Because with this X is increasing, the dryness fraction of the steam is increasing, and if dryness fraction of the steam is increasing means the quality is increasing, means moisture content is decreasing. There will be no effect on the pump work if you are carrying out the reheating. W net will increase because the turbine work is increasing. Cycle closed area is increasing, so W net will increase, quality will improve, moisture content will decrease, efficiency can increase or decrease, it depends on the reheat pressure. So option B will be the right answer for this question. Let us now move to next question, guys. Question number 17. The second law efficiency of a simple Rankine cycle can be increased, can be improved. What is second law efficiency, guys? Second law efficiency is nothing but efficiency actual by efficiency ideal. So if you want to improve this second law efficiency, this is like at a particular constant temperature range, this will be this will be maximum value. Okay, this is a maximum. Efficiency ideal or efficiency maximum or efficiency Carnot. So the efficiency of a heat engine with reference to the ideal or Carnot cycle efficiency, that is known as second law efficiency. So if you want to improve this second law efficiency, we need to improve the actual efficiency. And how we can improve the actual efficiency? By increasing the mean temperature of heat addition, T mean. अगर T mean बढ़ाओगे, so the efficiency will improve. By superheating, by regeneration, we can improve this efficiency. Let us see what are the options given. Using additional boiler. Additional boiler से कौन सा second level efficiency बढ़ जाएगी? No, the heat addition will increase, so the efficiency is not going to increase. This is not right. Regeneration. Second law efficiency, with the regeneration, yes, the efficiency will increase. Reheating, you cannot say. With the reheating, you cannot say that efficiency will surely increase. It depends on the reheat pressure. But with the regeneration, always mean temperature of heat addition will improve, and by increasing the mean temperature of heat addition, your actual efficiency will improve, and if your actual efficiency is increasing, your second law efficiency will also improve. So regeneration is the right answer for this question. Using one additional condenser, that is also not going to improve the efficiency. Okay, I hope this is clear to you. Let us now move to question number 18. Take the correct option for the exergy destruction in real Rankine cycle. In a real Rankine cycle, exergy destruction equal to 0 for compression in pump. Is it right? No. There must be some kind of exergy destruction in real Rankine cycle. He is talking about real Rankine cycle, and he's saying there is no exergy destruction. How it is possible? In a real, you know what is second law of thermodynamics? There must be exergy destruction in a real process. Exergy is always going to decrease in a real process. So this is not right. Exergy destruction will be 0 for compression in a non-zero for a compression in a pump expansion in time. This is right. Exergy destruction will be non-zero. He's saying non-zero. This is right. Exergy destruction equal to 0 for heat addition. This is also not right, because exergy destruction will be there in compression also, expansion also, heat addition also, because in real case there must be friction inside the various component, and in real case we are adding heat with some kind of finite temperature difference. So there are irreversibility in boiler also, there are irreversibility in condenser also. So these 2 points are not right. This point which is right, so we will go with this. Next question, question number 19. What is the effect of superheated steam? Superheated से क्या फायदा होता है बच्चों? What is the effect of superheated steam? If you are superheating the steam, means you are decreasing the temperature difference between the flue gas and the water. There is, in thermodynamics, the very beautiful concept we get from second law of thermodynamics. Entropy change. If you are adding heat at high temperature, if you are adding heat at high temperature, heat addition at high temperature cause in less entropy change. So if the temperature of heat addition is high, the change in entropy will be less, means irreversibility will be less, or exergy destruction will be less. That idea we get from the second law of thermodynamics. That's why it is better to go for more and more high temperature of the heat addition. Okay, and there is a limit of superheating, because superheating we cannot go beyond a certain temperature. So that's why what we do, sometimes we increase the pressure of the boiler. Why actually we go with very high boiler pressure? Why? Because very high boiler pressure, again your work output is going to increase. Okay, your cycle area is increasing and work output will increase, and your efficiency will also going to increase. So there is a limit to pressure also, due to the metallurgical limit, and temperature also, because if you go with very high pressure, your cost of the power generation, capital cost will increase. Okay, there is a term which is known as pinch point temperature. मैं एक term बताता हूं आपको, बहुत important है. Pinch point temperature. Pinch point temperature. It is a temperature between the flue gas minus temperature into the evaporator. Temperature of the flue gases minus temperature into the flue evaporator. So this is known as pinch point temperature. Okay, and guys, if this pinch point temperature difference, this is pinch point temperature difference. Okay, if this difference is less, this pinch point temperature difference is less. If suppose this is less, अगर ये less होगा तो क्या होगा बच्चों? Efficiency will be very high. Why? Because the mean temperature of heat addition is very less. The flue gases and the temperature to the evaporator, that is very less. So you are adding heat with very less temperature difference. So the efficiency will be very high. Okay, but that is going to increase the cost. Capital cost will also be high. Are you getting the idea? That's why we go for some kind of balance. ये zero नहीं हो सकता. Pinch point difference will always be there. Like it is not possible to have a same water temperature and same flue gases. In that case, how the heat transfer will be possible? Because some kind of temperature difference is required for the transfer of heat. So in real case, there must be temperature difference. But what we want less temperature difference. If less is the temperature difference, more will be the available energy, less will be the entropy generation, less will be the irreversibility, less will be the exergy destruction, more will be the efficiency. So that's why we are interested in lowering this pinch point temperature difference. But if you go into that lowering in pinch point temperature difference, cost will start increasing, efficiency will also increase, but we will go with some kind of compromise. Are you getting? So that's the reason we always go for more and more temperature of heat addition by carrying out regeneration, by carrying out superheating, so that more is the temperature of the heat addition, less will be the temperature difference, and less will be the irreversibility, more will be the efficiency. So superheating in a Rankine cycle results in what? Increase in thermal efficiency. Why? Because it increases the mean temperature of heat addition. मीन टेम्परेचर ऑफ हीट एडिशन बढ़ जाता है, सो एफिशिएंसी क्या होती है? बढ़ जाती है. सो ऑप्शन ए इज द राइट आंसर फॉर दिस क्वेश्चन. लेट्स मूव टू नेक्स्ट क्वेश्चन. In a Rankine cycle results in higher efficiency, regeneration. Rankine cycle में regeneration से क्या होता है बच्चों? What is the effect of regeneration in Rankine cycle? Higher efficiency, we cannot say all the time कि efficiency will be higher. Lower net work output, this is absolutely wrong, because if you are regeneration, okay, regeneration, yes, regeneration, not reheating. Regeneration, work output will be lower, absolutely it will be lower. With the reheating, work output will increase. So this higher efficiency, yes, with the regeneration, because T mean of heat addition will increase, because he is not talking about reheating, he is talking about the regeneration. So mean temperature of heat addition will increase, efficiency will increase, and work output will decrease. So option A itself is the right answer, guys. I don't think there is need to read other options. Okay, higher efficiency hoga, higher work output, this is wrong, because work output is going to decrease. W net kya karega? W net will decrease. Why? Because you are taking some kind of heat, some kind of steam you are taking from the turbine, and that steam you are mixing into the incoming feed water to raise its temperature, to raise its mean temperature of heat addition, so that less will be the irreversibility, more will be the efficiency. So regeneration results in more efficiency, less work output. So this is the option A is the right answer. Okay, so we discussed about superheating, regeneration. Reheating से क्या फायदा होता है? That also I think initially I discussed. I hope you are following all those things. Okay, now the similar kind of question. What is pinch point temperature? Pinch point temperature क्या होता है बच्चों? What is pinch point temperature? This is 21. So pinch point, difference between the temperature of the flue gases and inlet to the evaporator. So I think option B is the right answer. Option B is the right answer for this question. Chali, let us now move to next question. Some kind of data are given to us. This is question number 22. 1 marks question. The data at the inlet and exit of the turbine are given under steady state condition. This is the inlet enthalpy. This is the exit enthalpy. The loss in heat per kg of the steam is this. This is loss in heat per kg of the steam, 300 kilojoule per kg. If we neglect the changes in kinetic and potential energy changes, what is the turbine work? So guys, neglecting kinetic and potential energy changes, we can write this steady flow energy equation. H1 equal to heat lost equal to H2 plus turbine work. Yes or no? Neglecting kinetic and potential energy changes, the steady flow energy equation, we can write something like this. H1 inlet enthalpy to the turbine, heat lost, H2 plus turbine work. What is H1? Inlet to the turbine, 3250 kilojoule per kg. How much heat we are losing per kg of the steam? That is 300 equal to H2 exit enthalpy 2160 plus turbine work. So turbine work will be, okay, this will be negative, guys, because this is heat we are losing. This is heat we are losing. So this will be minus 300. Don't do these kind of mistakes. So this is heat rejection, not heat addition. Okay, so heat rejection will be heat lost by the system will be negative. So minus 300 you need to write. So 3250 minus 300 minus 2160. So if you will solve this, you will get the turbine work. Okay, so let me solve. 3250 minus 300 minus 2160, 790 is the answer. I'm getting 790 kilojoule per kg. Okay, so option C is the right answer for this question. Option C is the right answer. I hope this is clear. Chali, let us now move to next question, guys. Question number 23. What is the heat rate? What is the heat rate? Guys, there are two terms related to thermal power plant. One is steam rate. Another one is heat rate. how much heat is required, how much heat is added, how much heat is required to supply per kilowatt of the power produced. How much heat you need to supply for getting the kilowatt, 1 kilowatt of the shaft power. Okay, so net work output. So how much heat we need to supply per kilowatt of the shaft work, W net. How much heat we need to supply per kilowatt of the power output. So this is nothing but this is just reverse of the efficiency. So W net by heat supplied, that is known as efficiency. So what is heat rate? Heat rate is known as, it is a kind of parameter which generally we use for a power plant. If less is the heat required, means very less heat is required for get the shaft power, means your power plant is working very effectively. Okay, if more heat is required, means there are some kind of losses. Okay, there are high losses in your plant if you require very high heat to get the unit shaft power. So how much heat is required for getting the unit shaft power? That ratio is known as heat rate. So heat supplied in what? This is in kilojoule per second. How much heat supplied? Kilojoule per second. Divided by how much work you are going to get in kilowatt. Okay, so this is just reverse of the 1 by efficiency. It is a reverse of the efficiency. Okay, तो इसका यूनिट क्या होगा? हीट रेट यूनिट इज किलोजूल पर kilowatt second. Kilojoule per kilowatt second. So if you multiply with this 3600, so heat rate you can write in kilojoule per kilowatt hour, that is equal to 3600 divided by the efficiency of the plant. And more is the efficiency, guys, less will be the heat rate. If your power plant is having high efficiency, means heat rate will be less. If heat rate is more, your efficiency will be less. So this is known as heat rate. Similarly, what is steam? How much steam is required in kg per second? How much mass of the steam required in kg per second per kilowatt of the shaft power? Per kilowatt of the shaft power. Are you getting the idea, guys? How much mass of the steam required per kilowatt of the shaft power? Okay, so you can write it something like this, because this is the shaft power in kilojoule, because this is in what? This is in kg per second. Okay, kg per second. So you can write it as kg by kilowatt second. Kg by kilowatt second. This is a unit. But if you will multiply with this also 3600, इसको भी अगर मैं 3600 से multiply कर दूं, so the steam rate in kg per kilowatt hour, so that is nothing but 3600 divided by W net. 3600 by W net. Okay, what is W net? This is W net work output in what? This is W net net work output. Net work output. Okay, so the steam rate will be just reverse of the network output. Steam rate क्या होगा बच्चों? This will be just reverse of the network output. So this is network output kilowatt per, देखो this is in kilowatt, this is W net in kilowatt. Okay, this is in kg per second. So if you will balance the unit, write it here, because this is steam rate. ये क्या आपका steam rate है? This is also your steam rate. Okay, so how much steam is required in kg per second per kilowatt of the power produced? Okay, so this you can write it as kg by kilowatt per second. So if you will multiply this by 3600, you will get this in kg per kilowatt hour. So how much kg of the steam required for producing 1 kilowatt hour? Okay, how much kg per hour steam is required for producing 1 kilowatt shaft power? Okay, that is the definition of steam rate. So I hope these two terms are very clear to you. What is heat rate? What is steam rate? How much it is required for getting the unit shaft power? That is heat rate. How much steam is required for getting the unit shaft power? That is known as steam rate. Okay, so if you will answer here, the steam rate, heat rate. What is heat rate? The rate of heat input in required to produce unit shaft power. Option C is the right answer. Option C is the right answer, guys, for this question. Let us now move to next question, question number 24. The mean temperature of heat addition in the Rankine cycle can be increased by. How you can increase the mean temperature of heat addition, guys? How you can increase the mean temperature of heat addition? Reheating, it may be, but we cannot say. Maybe it may result in increase in mean temperature of heat addition. It depends on the reheat pressure. If the reheat pressure is it is close to 20%, 20 to 25% of the boiler pressure, then you will have more mean temperature. Efficiency will improve. it will be maximum. Decrease in the amount of heat added, you are decreasing the amount of heat added, so mean temperature will decrease. This is not right. Decreasing the pressure ratio, this is also going to decrease the mean temperature. Decreasing the turbine inlet temperature, that is also going to decrease the mean temperature. So there is only one option which we can think of in reheating the steam, so we can go with option A, which is the right answer for this question. Let us now move to next question, and this is the last question, guys, for the today's session. Question number 25. Decreasing the reheat pressure. Decreasing the reheat pressure, the quality of steam at the turbine exhaust. If you're decreasing the reheat pressure को आप decrease कर रहे हो, so the quality of the steam at the exit of the turbine is going to decrease or increase? Try to answer, guys. I'm waiting for your response. Okay, all the options are given, so that is going to increase only. How you can say, sir, we are going with the decrease in the reheat pressure, something like this. So this is reheating. Suppose we are going with low reheat pressure, something like this. So jitna low reheat pressure rakhenge, suppose this is the first case. Suppose you are keeping the high reheat pressure. So with the high reheat pressure, this will be the dryness fraction, something like this. With the low reheat pressure, this is high reheat pressure, P reheat 1, okay, and this is P reheat 2. And as you can easily observe, P reheat 2 is less than P reheat 1, so the dryness fraction is improving. With the lower reheat pressure, dryness fraction is going to improve, but efficiency is also going to decrease. So generally, we keep this reheat pressure reheat, we keep in the range of 20 to 25% of the boiler pressure. 20 to 25% of the boiler pressure. So this is boiler pressure, guys. This is PB boiler pressure. Okay. So increase is the right answer for this question. Okay. So I hope these 25 questions which we have discussed, guys, these are very much clear to you. So I tried to cover most of the questions. Okay, in those NPTEL assignment, I found these questions comparatively better. Okay, 15 questions we discussed. If you have not practiced earlier those Rankine question, guys, now I think you are familiar. Okay, and you got some kind of confidence in solving those kind of Rankine cycle problems. Okay, and guys, if you attended this session from the start of this class only, I can ensure you, like any previous year question from the Rankine cycle, whether from GATE XC, GATE Mechanical, and even in the upcoming examination, if you will try by all these concepts which we have discussed in the today's session, 100% you will be able to solve. Okay, बिल्कुल आप solve कर पाओगे all kind of numerical questions related to Rankine cycle. Okay, but further, if you want to practice more, we are going to share those 100 questions file with you. In those 100, the main important, which are comparatively difficult also, and slightly good questions also, I considered. I discussed 25 questions. Remaining 75 questions you will also get, and those you will be able to practice. Vijay Raju, it is related to what? Plasma range. I don't know, like in what context you are asking me this question. ठीक है, चलिए. Yes, thank you, Vijay Raju. Vijay Raju attended this session from the start only, and very good, Vijay Raju. You answered most of the question. Very good. Yes, Arjun, thank you very much, guys. देखो, अगर ये सेशन आपको हेल्प करता है तो दैट इज अ काइंड ऑफ सेटिस्फेक्शन फॉर अ टीचर. ओके. yes Ramakant, thank you. Yes Prashad, thank you. Yes, we will cover all subjects. This topic, I found this topic slightly different. Okay, and students generally hesitate in solving those kind of questions because they are comparatively lengthy. Even if you will sit for solving those 15 question, guys, you can try, you can check your time, you are going to take much more time. Okay, so I tried in covering all those questions in that minimum time. Okay, again we will meet and we will solve some more questions from the psychrometry also. I'm going to take actually the application part. Okay, thermal application. So cyclometry, I will take some question from the this NPTEL assignment. Thermal question and other subject question, they are comparatively minimum time we can solve those, but these questions are slightly lengthy. But then also I think most of the student attended this session, and you participated well, you tried all those questions. Good. Chaliye. So any query guys from your side, any technical query or any general query if you are having? Now I am able to answer all your queries. So if you are having, if you want to ask me anything, then we can spend next 1-2 minutes in discussing all those things. Otherwise I'm going to end this session. Okay. PDF you will get on your email ID. If you will link on the description of this video, you will find some Google form. If you will fill that, you will be easily able to get this PDF. Okay. Chaliye. Any query guys from your side? No query? Chaliye. So let me end this session, guys. Let me end this session. Again, we will meet and we will solve some more question. And if you want, like any special coverage, if you want related to any particular topic, it's my promise to you guys, before this GATE examination I will try to cover all questions related to that particular topic from the NPTEL assignment. But for that you need to message on any video on YouTube. Okay, on that YourPedia YouTube channel. If you will comment, sir, please cover those particular assignments related to that particular topic. So if you will mention something like that, then surely we will take your that request, and we will cover all those questions related to that particular topic also. Otherwise I planned some question from the cyclometry, some question from the this Rankine cycle we have discussed. And other than this I will take one class related to NPTEL assignment from auto and diesel cycle. So auto, diesel, Brayton, all three I will cover in a one day only, because Brayton cycle are not that much lengthy. Very simple, all those air standard cycle. So one more class I will take, and in that class I will cover auto cycle, diesel cycle, and Brayton cycle, all from the NPTEL assignment. In one day only we will able to cover all three cycles. Okay. And then cyclometry separate class I will take. Thank you very much. Have a nice day and keep preparing. Good luck.